So today we're going to start talking about MongoDB and kind of talking about NoSQL in general. We're not going to necessarily talk about the entire scope of NoSQL because it's pretty broad. But in general, anything, NoSQL is databases that are not relational. There are actually one or two NoSQL databases where you can actually use SQL. Couchbase is one of those. You can still write sort of a flavor of SQL, although it's not exactly SQL. But a lot of the databases in this group don't actually use SQL. And specifically, they don't use relational models of what you're familiar with, tables and rows. That's kind of that's one way to look at it, tables and rows, but there's some other ways to model how you store your data. Okay? So let's go over an example and see what this might look like. So if I think about storing orders in a relational database, specifically if I'm talking here, we maybe talk about MySQL, but this really applies to any relational database. I'm going to organize things with tables. So here I've got my orders table. Here I've got my order items table, right? So, and there's a mapping between those two things. So, right, every order has some order items, items that you're ordering, the products you're ordering is part of that order. So typically the way that we connect those two tables in a relational sense, you remember, is foreign keys. So these rows over here reference these orders by their primary key here, foreign key here. So that's typically how we would model this. So you can see the first order one has three items in it, and the second order has 2 items in it. Questions on this?
Nope.
Now, one of the things that I always notice when, anytime you throw this at a student the first time, and I'm sure most of you have run into this, you kind of look at this and go, what? Why? What's the connection to it, and why are you doing it this weird way, right? Because it almost seems counterintuitive. I mean, over time, people get used to it. It's like, okay, I can understand it. But it's always kind of a like, well, why are you doing this goofy thing of foreign keys? And part of that comes from the way that, honestly, the way that the hardware looked and worked at the time that relational databases were designed. At the hardware constraints at that point really meant that this was necessary from a performance standpoint, and just in terms of how the hardware actually had to function. So there wasn't really maybe a different option to do it efficiently. Okay, that isn't necessarily true anymore, which is part of why we're talking about alternatives now. But that used to be the reason that we designed it this way was because of efficiency type things. And one of those efficiency type things is with relational databases, typically you can say each row has a constant size. So I can say this row maybe occupies 20, 30, 40 bits. 40 bytes, and it will never be longer than that, which means that if I want to go to, say, let's say it's 40 bytes, and I want to go to the 5th row, well, I know that I just skipped the first 200 bytes. Does that follow?
Yeah.
That's not as hard and fast true anymore with relational databases. That was kind of a big part of the original design, but there are things that have been, with performance things, actually most relational databases do have variable size rows. Because if you say, well, a varchar, if I say everything's got a fixed length, I could say with a varchar, okay, I'll go ahead and reserve 200 bytes, right? I'll say, well, there could be 200 characters here, so we'll just make enough room for there to be 200 characters. As it turns out, that wastes a lot of space on disk, and with performance metrics having changed with hard drives, that's not as practical. That wasted space is not as is more of an issue now. Is more of a thing that we're kind of have a trade off. It's like, well, so what honestly happens? Let's say you have a varchar 200. It won't necessarily always allocate 200 bytes. So it usually allocates it roughly in powers of 2. So it might be that varchar 200 that you've allocated could be actually 2 bytes long, 4 bytes, 8 bytes, 16, 64, etc., up to 128, all the way up to 200. So it might not actually be, there might actually not be, that row might actually not be that full maximum size that it could be. So that's kind of the way things are right now with varchars. There's a lot of optimizations in there, but the theory was that every row should have a fixed size. And so with things needing to have a fixed size, that was not an option to take this data and stuff it into this table, because each order can have a variable number of items, right? Each order could have a variable number of items. So let's say I have, this order is 40 bytes and each of these order items takes up 20 bytes. Well, that drastically changes the size of a row if I were to include this data in here. Does that follow?
Yeah.
So I wouldn't be able, if I took this data and stuffed it into here, I wouldn't be able to say every row is this long.
Are you saying like Excel would be a flat table?
Excel is basically a flat table, right? Every sheet is a flat table.
Okay, that's what you mean by increasing the size of a row, like Excel style.
Well, I mean in terms of how many bytes the row takes up. I mean in terms of bytes.
Yeah, that would be a lot.
The binary thing. So the problem is that they needed to be that, and they also needed to be sequential. Because the other thing then you come into is, let's say I do stuff this data into here. Well, how much space do I decide to make? Do I decide to make enough for this having 2 items, 3 items, 5 items? What do I make that decision? Well, let's just say I decide, well, they can have at most 5 items, right? So I can plug that in here. Well, what happens if they need a 6th?
Yeah, it just wouldn't work then. So this NoSQL database isn't bound by data limits like that.
Well, there is a workaround. So I could say, like, maybe I put the data kind of underneath each row kind of thing. What I could do is say, well, let's not say it always has to be underneath. Let's say I usually want it to be underneath. That'd be more efficient. But maybe I say I have some sort of pointer, some sort of number where it could actually be, maybe the first 5 are underneath and with it, and then from there the rest are somewhere else, right? So I read through this and then I say, oh, well, there's another one. I go look somewhere else for additional items. I could do that. The problem is that then my reads become random. They're not sequential anymore, because I have to read the first 5 items here and then go read the 6th item somewhere else. So the other thing, that breaking these things up into 2 tables, it normally, in a lot of times, the theory is that it makes your reads always sequential. Does that make sense? I can read from the top of the table to the bottom of the table. Yeah, I'm not skipping around. You with me?
Yeah.
Now, in reality, there still is actually usually a lot of skipping around, because let's say I look at this order items table. Does the order of those have really any impact on the way that things should be displayed? Does it matter what order these rows are in?
No.
It really doesn't, right? As long as when I take the results, I just order them by the product ID, order ID, product ID, well, then I have a predictable order, right? So these could be in any random order. In reality, most of the times they are, right? So usually what ends up having to happen is we kind of have to go through and get all the order IDs and then match them up with the ones over here, right? And it ends up that we sometimes have some random access because of that. It may be that, especially if you're looking, hey, I only want the ones for customer ID 5, I'm not going to be getting all of the order items, right? So let's say I want to get the order items for customer ID 5. How would I go about doing that? Which I think I just realized my arrows are in the wrong place, because these lines should be connected back to the order ID, not to the customer ID.
What? Wouldn't you just do a foreign key, or what do you mean?
Well, let's say I know my customer ID is 5, right? How would I write a select statement to say, give me all the order items that belong to customer 5?
Wouldn't that select star from our where order ID equals customer 5?
What table are you starting with? Are you starting with orders, or are you starting with order items?
Orders.
Orders.
Yeah.
Okay. So you're saying select star from orders, but I said I wanted order items.
Oh.
Right.
So then we'd get order items, right?
Okay, so let's say I start with order items. Do I have the customer ID over here?
No, you don't have the customer ID.
Don't. So if I want to get all the order items for a customer ID, do I need both tables?
Yeah, because you need order ID and the order.
Right. So I'm going to have to do some sort of join, right? I'm going to have to say, let's join the orders and the customers together. And then now that I have that full list, I can now filter it by order.customer ID. Right? So I can say where order.customer ID is 5. But I have to join both of those tables together. Cool?
Yeah.
So what I mean then in that case, let's say I'm just getting orders for customer ID 5. Well, that's in all effects, that's basically almost a random collection of order items from over here, right? There's no way to know, just looking at this table, to know whether or not it's in the list, whether or not it's in your result set. So if I'm just looking at this, well, what do I have to do? I effectively have two options. If I say I join order items, I say from order items, join the customer ID, I have to go through the entire order items table. And for every order item, I have to go find out what the customer ID is. So I have to look at every single order item if I join that way. Does that follow?
Yeah.
But what happens if I join the other way? I say, let's start with orders, and then we'll join the orders to the order items. Well, it can go through the orders and say, for each of those orders, well, is the customer ID is 5? Well, if the customer ID is not 5, I can skip looking for order items with that order ID. But effectively, what I almost have to do is build up a list of order IDs from here that have customer ID 5, and then take that list of order IDs and go find the order items that have that order ID. Do you see that?
Yeah, and just out of curiosity, you do a left join on that one, or
it can be an inner join for this.
Okay, it should be, not can be, but
really
should be.
Matter. Left join, the only thing it would give you is orders that don't have any items.
Yeah, to get that along with everything else. I'm always worried about leaving data out by accident there.
But it's not really relevant to the example I had. Basically, it's the same problem if you do a left join or an inner join. the point is that you end up with a lot of random access. If you go from orders to order items, you end up with a lot of random access reads anyway, because you're not reading all of the order items. You're only reading the order items that have a certain order ID. So you're effectively ending up with a lot of random access here, but you're also, well, if you do it the other way around, right, you end up reading the entire order items table, right? So, and that's a problem, because if we think about, maybe we have, let's say this is a decent sized site and we have 1 million orders, okay? If I've got 1 million orders, how many rows do you think I have in my order items table?
Too many.
So I've got 1 million rows over here. How many rows do I probably have over here? Well, a good way to estimate it would be, how many items do you usually put in an order? Let's say you go to Amazon. How many items do you usually order at once?
A few.
A few.
I mean,
One.
Yeah. So, but let's average it out, right? So if we average it out and we say, or whatever other e-commerce store you're going to, usually you buy a few things, at the same time to get free shipping, right?
yeah.
So let's just be generous and give that a low number of 3, right? So we say on average, every order has 3 items in it, right?
Yeah.
How many rows does that mean the order items have? Yes?
3 million.
3 million. So we got 1 million rows over here and 3 million rows over here. Do you think it's a problem if I have to look at every single row here?
Yes.
Just to find the ones that belong to one customer?
That seems horrible.
That's obscene. Yes, that's obscene. So I definitely want to make sure that I do it in the other way around, right? So I start with the orders and look them up based on their customer ID. Now, from this side, I can use an index and make that faster, because I can index the customer ID, and then I just look in the index and I say, okay, I want customer ID 5, and it will give me all the order IDs from that index. So I don't have to look at, if I use an index for the customer ID, I don't have to look at the entire orders table. Okay, but I don't have a way to do an index over here because the customer ID doesn't exist there. Does that make sense?
Yeah.
So I can use an index to speed it up from this side. So let's say, however, that I don't. Let's say I don't have an index, right? If I don't have an index, how do I find the orders that have customer ID 5? Well, I have to look at all of those rows, right? So I'm looking at 1 million rows. So one way I'm looking at 3 million rows, one way I'm looking at scanning through 1 million rows. Which way's faster?
1 million.
Probably the million, right? So the order, even disregarding indexes, from this side to that side, this side's always going to be faster. But it's still going to be pretty slow, especially if I don't have an index. Does that make sense? So if I don't have an index, I have to look at 1 million rows. If I have an index, I basically effectively, the order of magnitude of work that it has to do is like scanning one row. Does that make sense? So adding that row in here is pretty close to making it a millionth of what the time it would take to go find the orders for customer 5. Does that make sense?
Yeah.
It's a little bit maybe more than that, but it's actually pretty darn close. Because again, the amount of time it takes to look things up in an index is roughly the amount of time that it takes to look at one row. So that's a drastic improvement if you just add an index in there. And indexes are really important in any kind of database you build. MongoDB has indexes as well, because it you get into the same points. But you kind of can see one of the issues there is I can't index this on the customer ID because the customer ID isn't there. Does that make sense?
Yeah.
but I can index this based on the customer ID. So those are the kind of things to think about. Even then, in the most optimized case, okay, so I can limit the amount of time I spend over here, but still when I go over here, can I use an index to make that part faster and not have to scan through 3 million rows? Because I still, the index made it faster to go find the orders. It didn't make it faster to go find necessarily the order items. Well, remember that when I say the customer ID, that gives me a list of order IDs, right? Using that index. Well, then is the order ID over here?
Yeah.
So could I index the order ID?
Yeah.
Okay. So I can index the order ID. So I can index the customer ID, and I can index the order ID. Putting those two things together is going to make it a lot faster. But there's still a very good likelihood that the amount of time this may take, it may need to look through several thousand rows, if not a few 100,000 rows. Just for looking up one customer's data. I may have to look for several thousands of rows just to look for one customer's orders. You see why that might be a problem, right?
Yeah.
So there's a lot to be gained by maybe we can maybe if we are okay with rows having a variable length, not having a fixed length, and not having a predictable order, if we can live without those two things of not necessarily having a defined order for the table and not necessarily having rows that have the same size, I can maybe merge these two tables together into one. Okay. So what we do with a lot of relational databases, especially MongoDB, which is what we call a document store database, we take that all and we mush it together into one object. So the example that we saw on the previous slide was how I would model it with a relational database. Here's how I'd model that in MongoDB. So here I have my first order. So it's got an ID. You'll notice it's called _ID. Do you see that?
Yeah.
Because in MongoDB, your primary key always is _ID. Can't be called anything else. Has to be called _ID. Okay? And that's one of the things that trips people up sometimes because they think, oh, I'm going to call this order ID or product ID. No, it has to be _ID. Okay.
So you really have just one huge complex table and no other tables.
I actually still have more than one table because orders and products are still separate. So I would still effectively, what we call this in MongoDB, we don't call it a table, we call it a collection. Collection's roughly similar to a table, but a collection contains these documents. Okay, so this is the order. This is the first order document. But I would still have other collections, so I would still have like a products collection. Does that follow?
Yeah, sure. The ID and the product ID, how does that number get in there? It's just generated.
So we can look at that. You'll notice here that it's not just a simple like 1-digit, 2-digit, 3-digit number, right? You see that?
Yeah.
It seems like it's almost random, which actually it is. This string is largely made up of partially made up of random data. And what you'll see in there is not just numbers, but you'll also notice that those IDs contain letters. Do you see that?
Yeah.
So they're hexadecimal. They contain the digits 0 through 9, but they also contain the digits A through F. So that means there's 16 possible characters that can be there. So it's base 16. So this is a base 16 number effectively. But it's, for all intents and purposes, it's random, and it gets randomly assigned. Anytime you say, I want to create a new row, a new document, as we would say, we give it a random ID rather than a sequential ID. Okay. So one of the outcomes of that is that the documents in a collection don't have a well-defined order. It's not, here's order 1, order 2, order 3, etc. They can be rendered in they can be stored in whatever order that the database decides to store them in. So you don't want to rely on that. You want to make sure you order your results anytime you display them. Cool. Other things you'll see in there. Okay, so we've got some JSON properties. You can see we've got the order date, the payment date, customer ID. These things I'm storing them as a string. As it turns out in MongoDB, you can basically store a timestamp in any format you want. Because there isn't really a necessarily, it doesn't have to be the same date. You can use really whatever date and time format that you would want, but I would recommend kind of sticking with that one, which is the one that we've been using with MySQL. Cool. Also, you'll notice the customer ID there is still there, but it's a different, it's another random number. One of the things you'll notice though, well, where is the customer information? Right? The customer has like a first name, some contact information, shipping details. Where is that? Well, when we looked at it here, where was the customer information? Well, it was over in the customers table, right?
Yeah.
So we do the same thing here. I treat the customer as another document and as another set of collections. Okay, so that doesn't change. That doesn't change there. What does change, though, you'll notice how I've put the items in. So rather than putting the items in a separate collection, I've actually embedded them into my document. Because as it turned, with the way that MongoDB works, you can have what we call subdocuments or arrays inside, can actually be properties and values within your database. So because these items only ever belong to one order and we never really reference the items outside of an order, I'm like, well, I might as well put that in here. Right. So sometimes we still will separate things. Sometimes we'll still have foreign keys like this, and you can see a product ID there. But a lot of times we can simplify things by taking documents and things that would be separate tables and joining them together into one thing. Okay. So effectively, you got the information for your first order here. So most of that's the same. I had an order date, a payment date, a customer ID. What changed was I took my items and I plugged them in there. You'll also notice as I did that, so I've got the product ID. I've also got the name of the product price, and the quantity, right?
All right, so there's no chronological auto number system that's auto incrementing. If that's ever applicable, it's always going to be this random string.
Right.
Right.
So your primary key, so the way you generate them with MongoDB, is this random string, which is what we call an object ID. We do not use auto increment with MongoDB, and it's actually not supported, and that's actually a majorly good thing, as it turns out, because auto increment columns are actually really bad, as it turns out, which is one of those things that people, it takes a little bit of time to learn, because it's like, well, they're the easiest thing to start with, but as it turns out, they're actually horrible in a lot of ways.
Yeah. Mr. Smith, what does Mongo mean? It sounds like the name of a gorilla.
I think Mongo is big.
Yeah, Mongo in surfer terms is like a big wave. They say like we're going to ride that Mongo wave. It's like a big wave.
Yeah. So it's like big database. Because Mongo is great for storing lots of data with lots of servers. So it kind of makes sense. Plus, you can have large documents, so they're bigger than what you might have in a regular relational database. So oftentimes that's one of those things that I can do differently when I'm working with a document database like this, is I can embed other documents. They don't anymore have to be scalar values. And the other thing you'll notice in there, so I've got the product name and the product price. A lot of times we don't put those in a lot of people don't put those in terms of this relational database. Why? Well, where are the name and the price?
In a different table.
They're in a different table. They're in the products table, right?
Yeah.
So as it turns out, anytime I want to display an order, actually, usually I can't even just use those two tables. Usually I have to join in the product table as well, right? Just to get those important pieces of information. Does that follow?
Yeah.
So by putting the name and the price, even though they're somewhere else, that means it's very easy to display the order, because I don't have to look up another table. So we call that process denormalization, because we're adding. Normalization is the process of kind of removing duplicate pieces of data. Denormalization is doing the reverse of that. So this is technically potentially duplicate data, the name and the price, because it's also stored somewhere else. But it does make it much quicker to query the data if I have a copy of it here. The other reason I might want to do that is, let's say the name of a product has changed. What happens if the name of a product changed, but I want to go look at an order from 5 years ago? Do I want that order from 5 years ago to show the new product name?
No.
Actually, no. I want it to show the name of the product at the time the customer bought it. Does that follow?
Yeah.
So it's actually better to have that copy, because it may be that the original data changes and we don't actually want to update this quote-unquote copy. We actually want it to stay what it was at the time the data was created. Same thing with the price, right? So here I know that the user paid $160 for these boots, right? So even if these boots change price, maybe right now they're $200 or maybe right now they're $100, I can still go in here and look at the price that the user paid. Does that make sense?
Yeah, I don't see how you could even do that with a relational database if you have the product name change and the price updates. Looking at historical information, it'd just be a huge pain. Huge.
Well, what you have to do is you have to add those columns here. So you have to add the name and the price to this order item. Does that make sense? You can play the same game and add duplicate data in here as well.
But it's so much harder.
It's not necessarily, I wouldn't say it's harder, but I would say it's more important to do it with a NoSQL database than it is without. So one of the things you really want to avoid with document database in general, MongoDB specifically here, what you want to do is avoid joins. Avoid joins like the plague. Because as it turns out, those can drastically slow down your queries. Does that make sense?
That's a movement I can get behind.
Okay, we want to avoid joins. That's one of our goals, and so that's why that's one of the reasons why it's more important to do it here, right? There's reason I would say on both sides, because you want that historical data to duplicate that data in both cases because of the historical reasons. That's a reason to do it in both cases. But the reason that we do it here is because it allows us to avoid that join with the products table. Does that make sense?
Yeah.
Okay. So that would be the first order. You can kind of see the data there. The second order would look like this. And one of the things you might notice there, if you pay close attention to the data on the first slide, you'll notice that the The first one is paid for. There's a payment date. This one doesn't have a payment date. Do you see that?
Yeah.
So with Mongo, I actually have a few options anytime I don't want to have a value for something. I could say payment date : null and set it to null, or I actually have the option of just removing the field entirely. You see that? So there is no payment date on this at all because it's not been set. Do you see that?
Yeah.
That turns out it's a little bit more efficient because it doesn't have to store the name payment date. And it can actually just be, it can be convenient from process perspective as well. So one of the things to realize there, if I'm having documents within a collection with MongoDB, they don't even have to have the same properties. So one collection may have property A, one document in a collection might have A, another one might have B, other documents might have both. So unlike where we were looking at relational databases, right? With relational databases, every row has to have the same columns, right? Every row has to have the same number of columns, right?
Yeah.
Yes.
I can't have like one has a name and another doesn't have a name column. It has some other weird column. Well, that doesn't apply to document databases. That doesn't apply to MongoDB. So I can have documents within a collection having different fields. So they don't all have to have the same fields, which kind of leads towards the idea that Mongo actually supports something called unstructured data, where the structure may not be well defined. It may not be the same for everything that's in there. So if you think about things like, let's say you're trying to do an online questionnaire app, there's a lot of different ways to build questionnaires, and a lot of questionnaires are very different. So what that means is their data is often has a very different structure. Or if you're having data submitted by users and they can kind of define and sculpt and define how that data is, they're basically defining, quote unquote, the schema for their data. You're not defining the schema for their data in some cases like that. So unstructured data typically is one of those things that we can't really handle in relational databases because they're so strict. There are things you can try and do, but large in part they're not designed for that and they don't work well with it. Whereas if I take something like this, it's actually really easy to implement structured data because I just put in, okay, let's put in a column, we'll call it user data, and the user can slap whatever they want in there. Does that make sense?
Yeah.
Because we can support objects and properties and they don't have to have the same value, they can just say, okay, I'll put wherever data I want in wherever structure I want. So that's one of those things. Okay. So let's talk about what NoSQL is. We've kind of started this conversation already. These next few slides are pulled from this article, What is NoSQL, which I put on Perusal for you guys to read. But there's some quotes, some part, a section of that I wanted to go over piece by piece. So what is NoSQL? When people use the term NoSQL database, they typically use it to refer to any non-relational database. Some might say that the term NoSQL stands for not only relational, or I think not only relational is usually the one I hear, where typically will be not relational. Yeah, not relational or not only SQL. Because there are some databases that kind of have a hybrid sort of model where you can do a little bit of both. But the general term is that it's not a relational database. Either way, most people agree that NoSQL databases are databases that store data in a format that is different than relational tables. So that's what we kind of saw in the previous example, is that rather than storing things in tables, we're storing things almost an array of objects is basically the way it works out, which we call collections. Cool.
Yep.
So the whole point is that it's stored in different ways, and there's actually more than one kind of relational database, NoSQL database. The main three that exist out there are document stores, which is what MongoDB is. There's also key value pairs. The most common one that people use in there is something called Redis. So Redis is a key value pair database, and basically the way that works is you say you can kind of think about it as a dictionary or an object, and then basically you say here's the name of the key. I'm going to put whatever value I want in there.
But whenever you restart that server, all the data disappears.
With Redis, I believe so.
Yeah.
Redis, which is where people use it for things like caching. There's a lot of purposes where you care about having temporary data, which is basically where that's for.
It's really cool though.
But there are databases out there that are persistent. So for instance, Firebase, which a lot of people use for Android apps. Firebase is a key value pair, but it's persisted. The data doesn't go away when the server shuts down. So basically the way those key value pairs work, it's just one giant object with keys and values for that. So that's another kind. There's a third kind of NoSQL database, which is graph databases, and graph databases are very different. Very, very different. The way that their work is they rely largely on something called graph theory, which is kind of a discipline of math, which actually turns out has a lot of applications in computer science. But basically you have kind of nodes in the graph or vertices, and those are almost a little bit like your rows or your documents. And then you have the edges, you have lines between each of those nodes, and those represent kind of relationships, but they can be more complicated than some of the relationships that we have in your regular databases that you're familiar with. Graph databases are actually really, really cool. I did see a video about one, and there's some really amazing stuff that you can do with graph databases. Neo4j is I think the most popular one of those. But they are very weird, and they're definitely outside the scope of this semester for sure.
What type of companies use that?
Kind of companies that really need to talk about relationships that are more than just the first degree. So some things that are, it's kind of easy to answer things with your regular databases like, well, how many orders did customer 5 buy, right? So I can say that they bought 5, or I can look at, how many orders did each customer buy? But what if I want to say, things more complex to the, like, let's say I want to know what browsers they were using when they bought the orders, or what country they were from, how many of their friends bought the same product. That's where things start to get weird with your regular relational databases.
Oh, okay.
Is where we have kind of, let's say 5 degrees of separation from Kevin Bacon kind of thing, right? Those kind of queries are really hard to build. But graph databases are really good for those kind of things. Okay?
Yeah.
So those exist there. I think it's something to look into. It's largely the place where they come in is where you're trying to do metrics on and doing a lot of statistics on the data that you have and trying to draw meaning from that, which honestly a lot of companies benefit from, but isn't necessarily their core market per se. So it's graph databases are really good for things where you want to do a lot of data analysis, but they're a little bit harder to maybe get used to because of all the weirdness that they introduce. So we're gonna talk about Mongo is just the one that we'll talk about, which is a document database. So a common misconception with NoSQL databases, because of the name, especially because they're not relational databases, is a lot of people think that they don't store relationship data well. And specifically, part of that is that Mongo, for instance, doesn't have foreign keys. They don't exist. Which might seem like a really weird thing, right? Because pretty much almost every table that you created there was some foreign key either coming from it or going to it, right? With the databases that you built. It's very weird for there not to be a foreign key. You also might look at, the example we just did. Is there a foreign key in there? Does this document include foreign keys?
No. I mean, the items.
Is this customer ID here a foreign key? Is that product ID a foreign key?
Yeah, kind of.
Kind of.
It kind of is. It's relational data, actually. I'm relating this order to another customer, and I'm also relating it to products. So in some ways, I kind of have a foreign key. The difference is that while I can store that data, I can store the primary key. I can store whatever data I want. In this case, I'm storing the primary key of some other document. So effectively, it's kind of a reference to another document. And I'm treating it as a foreign key. That foreign key is not enforced. So if I delete a product, this order doesn't go away and doesn't have to go away. Does that make sense? So what exists in our relational database is actually what we call a foreign key constraint, where it says that it has to be obeyed, that this number has to be a primary key for another table. Troy, you were saying something?
Did I?
Oh, okay. I just saw your light blink.
I must have accidentally pressed it.
So in some way, right, we sort of have foreign keys. They're just not enforced. Do you see that? So there's not a formal foreign key structure or foreign key keyword in Mongo. Got it?
Yep.
But that doesn't say that we can't use that technique, and a lot of times it is used. So that's one of those things that people get confused. Is that it's like, well, they can't store relational data because they don't have foreign keys. Well, they can. They just store it differently. So you can use foreign keys kind of the same way that you did before, but oftentimes it's stored in a different way. So, for instance, one of the ways that we can store relational database data is just by nesting it inside of another document. So, for instance, if I was looking at here, right, I have to have this order ID column, right? Because otherwise I would never know what item this goes, what order this item goes with, right? So the relational data between these two things is stored in this order ID column. Got it?
Yeah.
Well, notice I don't need that order ID field here. Why? Well, it's already nested inside of the order. Do you see that?
Yeah.
So I can eliminate the order ID in those nested documents because it's kind of implied. In fact, I wouldn't want to put it in there because I'd have a lot of duplicate data, because this one says what the order ID is. If I put the order ID in all of these, well, then that's majorly duplicating, right? Because I can just look up here and find it. So those relationships, those nested relationships, that kind of is another way to store relational information, right? That it's nested inside. So that's one of the things to, you realize is that there are more ways than just foreign keys to store relationships. Got it? Relational databases kind of get that name, but that's not really so much that they're the only ones that can store relational data. It's just that they store it different. That's where I was. So they can store relationship data. They just generally often store it different. In fact, a lot of people find comparing SQL databases and modeling between SQL and NoSQL database, it's actually oftentimes more intuitive to model relational data in NoSQL databases like Mongo, because you don't have to split that data between tables. So it's actually easier to nest and think about the order items as nested documents rather than thinking of them as some separate document. Does that follow?
Yeah, Mr. Smith, I looked ahead in the slides, and
yeah,
I don't see a program like the Oracle MySQL with the dolphin, mostly white background on it. What do we use for this? What creates these JSON things, JSON objects we got here?
So there's 3 tools that you can use to connect to a MongoDB database, which we'll talk about towards the end of this. One is something called Compass. There's also a shell, and you can also use Node to connect to it. So Compass would be the one you're kind of thinking of. Would be the similar to Workbench. So we'll talk about that in a bit.
Okay, all right.
So, but today I'm mostly focused on, right now I'm mostly focused on theory, to kind of explain why is this that we're doing this, and what are things you need to be aware of as we're transitioning. Because one of the things that you don't want to make the mistake is let's say I take my ERD and my schema as it is, and I'm just going to plop it over and call it tables and columns, right? Call it columns. Instead of calling it tables and columns, I'll call it collections and fields, and collections and documents and fields. So you really have to rethink how you model those relationships and how you store the data. Cool. So oftentimes that becomes easier to model because you don't have to split the data from one table to another. So orders is a common place where that's easier to do. A lot of systems have things like tags, right? So usually like a blog might have tags connected to it, so you can search it based on a tag. Now, if I want to have, let's say, a blog that has 5 tags, how do I model that with a relational database? Well, I need a blogs table, right? But I also need a blog tags table. Because remember, anytime I have to one-to-many relationship, that means I need 2 tables. Does that follow? So I'd have to have a blog and a blog tags table. That's kind of weird and honestly a little bit inefficient. I like to kind of merge those 2 together, so I can have my blogs have tags instead of like throwing my tags into another table. Well, I can just do that in a NoSQL database. I can put that in Mongo. I just say, hey, tags is an array. So tags just contains an array of strings, and those are the tags. Does that make sense?
Yeah.
So a lot of times things like that are actually much more intuitive in terms of relationships, because you have arrays and you have objects that you can put inside of documents, and that can be oftentimes a lot simpler than making additional tables. So NoSQL databases emerged just to give you some history, emerged around the late 2000s. As the cost of storage was really going majorly down. At that point, the need and the days of needing to create complex, difficult to manage data models simply for the purposes of reducing data duplication, which is a big part of what relational databases are about, is reducing duplicated data. That becomes not as important as it is, not as important as it used to be. So things like, adding the name and the price in there into the items is a lot more practical now, because storage doesn't matter as much. So one of the things that started flipping is that developers, rather than storage, are the primary cost of software development now. That didn't used to be the way that way in the 70s and the 80s and the 90s. In the 70s and the 80s and 90s, your costs were largely dominated by hardware costs. Your developers were, by comparison, much cheaper. Does that make sense?
Yeah.
And it's not necessarily to say that and it's not necessarily saying that the developer salaries have changed. It's the fact that the hardware, what the hardware you needed to get, cost a sizable chunk of change to buy a hard drive, right? And a hard drive was a rather large piece of equipment, to the point that a lot of times, basically in the 70s, developers didn't, software engineers did not have individual computers. I didn't, if you had 10 people on your team writing software, they each didn't have their own quote unquote computer. They kind of shared resources because the hardware was so expensive. So you might have one computer for 10 and one hard drive per 10 developers because of the costs. But nowadays, pretty much everybody gets their own computer, right? It's unlikely that you're going to be sharing a laptop with one of your coworkers, right?
Yeah.
But that would have been unheard of in the 70s and 80s. To say everybody gets their own laptop? What?
They would have been freaking out.
Yeah. Everybody gets their own computer, because laptops weren't really as much of a thing anymore. They had desktops, but, and the idea of a portable computer was something the size of a suitcase, a big, heavy suitcase. So it's, it's a different story. So part of that change is that NoSQL databases are not as optimized for storage. They are gonna, because we're storing things, the way we're storing things, it's not going to be as efficient in storage space, but they are, however, optimized better for developer productivity. They're better optimized for building software quicker and adapting to changes and requirements as you need to. So if we look at kind of a graph over time to illustrate that point, you look back in the 60s, the 70s, this is a hard drive, right? This is a 250 megabyte hard drive. See that?
I think you said that weighed 500 pounds, didn't you?
Yeah, something like 150 pounds, fully assembled. This is not fully assembled, because you see they're still working on it. But it's pretty darn big. Versus what do we have now? We have these M.2 drives, right, that are pretty tiny by comparison, but that's a terabyte of storage, right? And this costs a fraction of what that did, right? So this might be something I can get for $100-$200. This at that time, if we were think about dollars in that time, this might be several thousands, or adjust for inflation, that could be quite a bit. So storage, you talk about cost of megabyte in US dollars. We kind of started up here where it was pretty darn expensive, and then at some point here, 90s on into the 2000s, it just went down. You see that?
Yeah.
So that used to be something that we really, really cared a lot about. And I did mention this earlier in the course, storage space used to be something that we optimized. It's not really something we optimize anymore. We still care about, memory space, but we care very little about how much space something takes up on disk, to be blunt. because it's easy to buy another 20 hard drives and slap them in your server, right? Or buy another 5 servers. Buying the hardware is cheap by comparison, and especially compared to developer hours. So as storage costs rapidly decreased, the amount of data applications needed to store and query really went up quite a bit. So, and the data that came in was in all sorts of different shapes and sizes. We had structured data, we had kind of semi-structured data where it's largely the same but with some differences, and then you have like polymorphic data, which is things if you're thinking about class hierarchies and inheritance, that can be something that is actually really hard to store in a database. If I say I have like, here's my animals, and underneath that there are cats and birds and dogs, oftentimes those different child kind of classes have very different fields and pieces of data. Or if I think about shapes, right? Well, what data do I need to store for the size of a square? How many fields does that have?
4. Well, actually, just 1.
Just 1, right? Just 1. Okay, so I only need one number for the size of a square. How many numbers do I need for the size of a rectangle?
2.
2. Okay. What about the size of a circle?
4?
I just need 1, right?
Well,
which is the radius.
Oh yeah, I guess.
But if I wanted to know the position of the circle where the center is, I might need to add an x and a y, right? So then I might have 3. If I want to store how big do I want to store a, information about a triangle, how many pieces of data do I need?
3, maybe 6 if you're getting the angles.
It turns out I can do it with 3, generally speaking. So I can, as far as that's concerned, I can have the 3 sides, or I can have the 3 angles. If I have, I take that back. No, you need the 3 sides. If you have the length of all 3 sides, you can actually figure out the angles, as it turns out.
Okay.
But if I remember right, if you have the 3 angles, you don't actually know what size the 3 sides are. You just know relative, like which ones are, what ratios they have. So you might need the 3 angles plus, or 2 angles plus 1 side. There's a few different ways to define it. But typically you need basically three pieces of data, and that may be a mix of angles and side lengths, but typically 3 pieces of data. So if you're thinking about those things and you're thinking about how to do class hierarchies, if you're thinking object-oriented programming, those can actually be really hard to store in a relational database because of that. And you have to kind of, if you're going to do that, you have to create your rows in such a way that they can store the data for any class. Does that make sense? And you have to kind of future-proof yourself and reuse things. So NoSQL databases really allow you to store what we'd say huge amounts of unstructured data, and that gives you a lot of flexibility. So that's really where they become helpful. Is A, you have lots of data, and B, it's maybe not as structured as maybe it's not strictly structured. A lot of places that comes in where you have hierarchies, a specific example where that comes out is oftentimes with users. So let's say I have different kinds of users in my system. My customers might have certain fields, and my employees might have different fields, right? So oftentimes, what I have to do with modeling those different kinds of user data, oftentimes it means creating more tables or having to kind of jump through hoops to try and figure out, well, the customer and the employee, merging them in together, because we may need, for instance, let's say we have the employees. Well, there's certain information that's required, like potentially if you have an employee, you might need to know their social security number, right? and other identifying information like their driver's license number, etc. You might need to know their bank account so you can do direct deposits, all those kind of pieces. But that would be very weird to have that data on a customer. Does that make sense?
Yeah.
To store like their social security number and those kind of things that you would keep on an employee. So similarly, let's say I've got employees, or let's say I've got customers. Typically, customers will we want to store things like their home address and their shipping addresses and their billing addresses. Well, it's very weird to have a billing address and a shipping address on your employees, right? That's not the case. They don't have a billing address and a shipping address, right? So that's one of those places where, even just talking about your users, oftentimes they don't necessarily have the same structure based on what role they play. Does that make sense?
Yeah.
So that's actually one of the most common places that you see kind of semi-structured or polymorphic data is when you're talking about users. Okay. So another thing that's led to this drive towards NoSQL databases around the 2000s, something called the Agile Manifesto was written, which was kind of the birth of what we call agile methods or agile methodology, which is encompassed a lot of different techniques and ways of writing software. But I can kind of, let me pull up the manifesto when we can look at it. So this was written in I think 2001, according to that. I think that's right. And it kind of, there's 4 pillars to agile. Individuals over individuals and interactions over processes and tools, which means that you value, working with people rather than having like, here we formally documented how we do this, and so we always do it that way. Other things, working software. Well, working software is more important than documenting everything and having everything written down. Okay. Collaborating with the customer is more important than specifically, negotiating over the negotiating the contract with them and saying, well, we'll only agree to do this. We'd rather just deliver them the thing that they want, or, as our understanding of what they need changes, will we adapt to that? And basically responding, this is kind of encompasses the whole thing, is responding to change over following a plan. So a lot of companies in the software development world are practicing what we call agile now. And part of that, as you can see, there's kind of several pieces to it, but the main driver is kind of listening to the customer and finding out what they need and changing our software as we find new information out, rather than strictly defining, here's what we're going to build at the beginning, going and building it and then delivering it to them, which is what you would refer to as maybe waterfall. So that's led to a lot of changes and rethinking of how we build and develop software. Relational databases were a good fit when you could formally and well define what the requirements for the application and what it needed to do at the beginning. But nowadays it's hard to say at the beginning what the application needs to do. It usually changes somewhere in the middle as you're building it, right?
Yeah.
And sometimes you've already had this problem of you design way too much stuff at the beginning, and then you find maybe you don't have enough time to complete it, or just other things change about what's the goal in between. So that's an important part. And one of the things with relational databases is they're kind of not really good about adapting to change. It's not an easy thing necessarily to say, okay, well, let's just add a whole nother 5 tables, right? Or let's add tags to our blog post, because now I have to add a whole nother table just to adapt for that one tiny piece of additional data. Does that make sense?
Yeah.
So oftentimes you find yourself maybe making some major re-architecting, even when it's just a tiny little change. Your data type changes, or a column becomes optional that used to be required, or becomes required that used to be optional. All of these kind of things are really can be hard to deal with in terms of a relational database and the strict structure that it has. So with the current world, we really need to be able to rapidly adapt to the changing requirements. We need to be able to start building an application and then iterate quickly and making changes throughout the stack, throughout our application, as we need to, and that goes all the way down to the database model, and that includes things like being able to test at any individual point and easily being able to on-ramp new developers, and things like that. So NoSQL databases make it a lot easier to have that flexibility, because with the way things are not as structured, as you saw, we can have documents have different fields. Not all fields have to be there. They don't have to have effectively the same columns for every row. That unstructured nature of the data, we can adapt to those changes much easier, because, for instance, let's say, well, I add some additional data. Well, now that appears on the newer documents, and the older documents, well, maybe they don't get updated. They get updated when they need to be, when we choose to update them. Versus if I say I want to add another column to a table, well, now every row has to have that column, and now it may need to even have to have a value. Does that make sense?
Yeah.
Something like that.
Huh? You're saying something like that?
Yeah.
So that's kind of the overview and where these have come in from a kind of historical standpoint. I want to talk about we've started this conversation, but specifically pointing out what some of the problems are with relational databases. So relational databases were designed for a world where a few things were true. Hardware was very expensive, both in terms of your storage and your memory. So they were designed in the 70s and the 80s, and we're still using them. They're still being adapted, but primarily they were designed, back at a time when, hardware, you saw a side of a hard drive was 150 pounds, and that one hard drive was shared between, 10, 20 people, and it was locked in a room, and your computers were large in part, you had these mainframes and such that were, the size of a room for a single computer, right? So they were designed into that space where hardware was really expensive, was big and expensive. Software engineers in relationship to that were actually very cheap. They were much cheaper. It was much cheaper to hire more software engineers than it was to buy another computer. Does that make sense?
Yeah.
So in these days we kind of talking about having enough people to maybe do the work. Back then it was actually having enough people to keep the computer busy. Right? So they would hire more people because the computer's like, well, it's sitting around doing nothing. That's lost money, right? So our goal back then was to keep the computer busy and to do as much work in with that computer, so it's not sitting idle or wasting electricity, or not getting orders processed and yada yada. Oftentimes back then, the software engineers were seasoned employees of the company. Back in the 70s and 80s. Especially early 70s, early 80s, a lot of software engineers weren't college grads. They weren't computer science grads. They weren't usually people that had gone through and got a degree in computer science, because computer science degrees didn't really exist yet. So a lot of them were employees that were already at the company and been there for a decade or more, and they really understood the company's business really well. They maybe would have been new to the technology, but they understood the company well, and oftentimes they were things like scientists and accountants and such. They understood how to do the billing in a paper sense. So they were translating that knowledge that they already had to the software and the databases that they were building. It's not like we have today, where a lot of times developers come into a company and like that's their first day into the company. They don't know anything about what the business is. Does that make sense?
Yeah.
So back then they usually had a pretty good idea of what the business did, because they'd been working in some other job before they became a software developer, software engineer. And generally speaking, any system that you had less than 100 concurrent users. That was a lot. To have 100 people on the same system would have been huge. But that's change right now, right? 100 users on a website at the same time, that's like a rounding error. Right? If you think about Facebook, right? How many users do they have online at the same time? And remember, you got to count everybody who's getting notifications because they're effectively on the system. So you got millions, probably billions of people on Facebook at once. Because again, you got to count everybody who's just got their phone off but getting notifications from Facebook. So, 100 people, and that being the max, right, that a system had, that's a whole different story. So they didn't need to handle a whole bunch of people on that system at once. And usually it was less than 10 people that were using the computer at the same time. The internet also really did not exist. They were starting to see networks, there was different experiments with that in those early decades, but there was no concept of the internet, which also meant that these early databases did not have websites attached to them. Let me repeat that. Like, these early databases did not have websites attached to them because websites didn't exist, right? Nowadays, it's very rare that you interact with a database directly, right? We generally interact with them through a website. Does that make sense?
Yeah.
So the databases of that day, and databases kind of still do, have to provide a lot of the things that your web application now does, like validating the data and providing users ways to perform the CRUD functionality and interfaces and such. They had to provide all that UI because there wasn't another thing on top of it. The database was it. So other thing, I kind of mentioned this already, hard drives were a big deal there. And hard drives, largely magnetic, either they were tape drives or they were disks. But they could only efficiently perform sequential reads and writes due to something called seek time. And because they were mechanical, because magnetic drives are mechanical, what I mean by seek time is the amount of time that it takes for the arm, which reads it, has to get to that place on the disk or the tape to actually read the data. Does that make sense? Like, there's physical travel time involved. And because of that physical travel time, to get to where the data is stored, you had to really be efficient about that. Efficient about the travel time. Does that make sense?
Yeah.
So that's a big reason why relational databases are structured the way they do, is to try and encourage those sequential reads and writes, and that's also why they care about the having the idea of every row having a fixed size, because then you can kind of predict and know where you're going to seek to. You don't have to read all of the data in between to figure out where it is. And also, so given all that, given that the employees knew the business really well, oftentimes the scope of the application was really small because the only people that were using that system were generally the employees at the customer. So they were filling out orders and processing inventory and all kind of things, mostly for sometimes mostly brick and mortars. There were still even in those early days, we started seeing airplane bookings being online. But even with that, you're talking about a relatively small number of users, and you understand the problem, right? So it was pretty common to be able to make a set of requirements for the application, and everybody would understand what that is, because everybody had been working there for 10 plus years, and they understood the language that everybody was talking and the expectations. So those were pretty easy to define and know and be static. They probably weren't going to change 2 weeks from today. Does that make sense?
Yeah.
But that's not, if we look at all of those things, those are all different now, aren't they? Hardware's cheap. Software engineers are expensive, more expensive than the hardware. Most of software engineers are complete noobs to the company that come in. They don't usually understand the business from the get-go. 100 users is change, so we're talking much bigger. We have the internet to contend with, and pretty much anything we have with the database is going to in some way interface with the internet because we're going to throw a website on top of it. Hard drives, you've seen those largely been replaced by solid state disks, and solid state disks aren't mechanical, so they don't have that seek time limitation of not being good at reading data that's not sequential. Okay, and requirements as it stands, they change very, very often, and that's why we switched largely over to Agile to try and adapt to those things. Okay? Questions?
Nope.
So databases today, we need to handle thousands and millions of concurrent users, not just not just 10 or 20, but thousands and millions. They need to also be able to handle millions and billions, sometimes even, of records. We're talking about orders and other things. We need to be able to deploy them to multiple geographically distributed servers to handle global traffic. So if I have a business that's selling internationally and even just across the U.S., it's not really practical in terms of performance oftentimes to just have one database server. So even if I'm just talking about the US, I might have one database server on the West Coast and one on the East Coast, even for a relatively small company, because companies tend to have offices across the nation. And if I'm doing anything internationally, if I say I'm doing business in China and the U.S., there's no way I'm going to be able to get away with just having a server in the U.S. Does that make sense?
Yeah.
It would be too slow. So I need to be able to have a server. If I'm doing business here and in China, I need a server here, a database server in here, and a database server in China, and wherever other countries I'm dealing with. So Australia might get its own. South America might get its own. Africa might get its own. Europe might get its own server. So I need to have a lot more than just one database server managing my data that my website is connecting through. Does that make sense? So that's really important. But the original databases, there was only ever one database. Like the database was running on one computer, right? So databases kind of at their core almost are designed, relational databases were designed to work in that space where there was one database. The database is on one computer. Okay. Hardware is cheap. Developer hours are expensive. We talked about that. We've got SSDs, flash memory, RAM. All of those make it easier to do and efficient to do non-sequential reads and writes. It doesn't just have to be sequential because we don't have those mechanical pieces in there. Large in part, our business requirements are not well understood, not well defined, and they're oftentimes changing. I can't tell you how many times that I've worked on a piece of software and found out a week or two later that the customer or the clients or whoever's giving you the requirements, your stakeholders, have changed their mind. And changed their mind oftentimes in pretty drastic ways. Okay. So our databases today need to really be able to adapt to those things. And I would say that relational databases don't deal with those things well. Aren't really built for that. So let's talk about some of those things in relational databases that we run into that they're actually, as it turns out, problems. One of them is auto increment, actually. I mentioned this earlier. Remember, Paul? We kind of brought this up when we were looking at the example. Part of the problem with auto increment is that it requires synchronization between your database servers. So if I use auto increment as my primary key, well, let's say I want to insert a record, right? And let's say I'm going to insert, I'm in US, I'm going to insert it, but I have 5 servers across the globe. Well, can I just insert the record into into my US server and be done?
Yeah, I see what you're talking about. It would just do the next sequential number.
It has to go check with all the other servers and say, okay, I want to use the number 100. Is that okay? It also has to say to all those other servers, you can't let anybody else use number 100. Does that make sense?
Yeah.
None of the servers can work in isolation because anytime you want to insert data, you have to talk to all of them and say, this number is reserved. Don't give it to anybody else. So you have that problem. That actually is a very big synchronization overhead because, again, every time you insert a record, I've got to talk to all the servers and wait for that. So that means I have to wait for my connection to all these other countries or all other places around the globe, and that's really oftentimes can defeat, synchronization overhead can really start to defeat the whole purpose of having different database servers, right? Because the point of having multiple database servers is you reduce the distance between your user and the data, so there's less lag and things like that. The other thing that happens is that, let's say I'm using auto increment, it's actually really easy for attackers to guess what those numbers are going to be and predict them, right? So if I know that my user ID is 27, what do I know?
It has to at least be higher than 27.
Well, I know that you're backwards. If my user ID is 27, what do I know?
There's probably a user 26, 25.
There's probably 26 other users. And so I can guess those numbers 1, 2, 3, 4, 5, 6. And I can, if I'm dealing with the address bar, I can just type those in, right? Or if I'm working with my hidden fields, I can just change the value in the hidden field and guess that, well, if 27 is good, well, 3 is probably some user. Does that make sense? So it can be very easy for attackers to just randomly guess numbers, or even they can just say, well, I don't even know how many users there are. Let's just start with 1 and I'll count up to 1,000 and see how many users I get. Right? I can just try them all. So that's a problem because users can just guess IDs and see if they work. Does that make sense?
Yeah.
Because you can try it with trial and error that way easily. It also reveals how much your website's being used. It reveals your usage statistics, which you might want to keep private. So let's say I use an auto increment. I've got a blog, some sort of social media network, and my users are able to make posts. So let's say I make a post on Monday, right? And I look at that post ID, and it's 500. Okay, cool.
Mm-hmm.
Now I make another post on Tuesday, same time, and the ID is 600. What do I know?
About how active the site is, yeah.
Exactly. So just from that, looking at my post ID on Monday, my post ID on Tuesday, I can know that about 100 posts have been made on Monday in that 24-hour period. Does that make sense? Do the same thing for make one post on the first of the month and make another post on the next month, the first of the month. So first of November, 1st of December. I can see, how many posts have been made in that month. So that can reveal a lot about how much your site is being used. Do you think that might be interested to? You think your competition might be interested in that?
Of course.
Probably. There's, or if I'm looking at, say, banking data, maybe I can reveal some things there. Especially if we're able to drill that down to see, oh, this user's made, this account has made 100 transactions this last month, or 20 transactions yesterday. I might be able to use that data, right? So we'd rather like to keep that private. How much is our website being used? We don't want attackers to be able to guess those IDs. Okay. So auto increment for those three reasons are really a bad thing. It doesn't matter if you're using relational databases or using NoSQL databases. Auto increment's bad. Does that make sense? Can you follow? So, and it also means that there's a bottleneck anytime I want to insert data, because I have to kind of I can't I can't figure out what that ID is offline. Right, so I kind of send the server there and then wait for it to come back to know what ID I actually got, right? So there's a lot of places that becomes an issue, and the offline thing there as well. Let's say I'm trying to build a mobile app that needs to work across the globe, and especially in places where the internet's spotty, right? So if I need to support offline activity, that makes it a lot harder, because I can only insert a record into the database when I have a network connection. Does that make sense?
Yeah.
So that's another thing where that kind of falls down. So foreign key constraints, another thing we use all the time, at least you've already used, suffers from some problems as well. So just like I talked about, auto increment requires communication between all the servers. In order to enforce a foreign key constraint, you also have to synchronize the database servers. Because if I insert, update, or delete data, right, I have to know all the data that's there. Does that make sense? I have to know if it's violating the foreign key constraint. You with me?
Yep.
So, for instance, let's say a user has orders and there's a foreign key between those two. If I delete a user, do I also have to delete their orders? Well, yeah. So what happens if, I'm trying to delete the user, but on another server over in another country, or over on the other side of the US, simultaneously I'm trying to add a order for that customer, right? That's going to conflict. Does that make sense?
Yeah.
So synchronization there is required for the foreign key to be enforced. I don't need that is if I don't enforce the foreign key. So if I have the value stored, but I don't enforce that constraint, then I don't have that synchronization overhead. That synchronization overhead purely comes in when I try to enforce validity on that data. Okay. Also, the other thing that happens there, because of those foreign keys, anytime I read or write data, not only do I have to lock and prevent changes to the table I'm looking at, oftentimes I have to prevent changes to multiple tables. So for instance, if I want to query, we were talking about orders, right? And I want to show you your past orders, I have to look in which tables? Well, I have to look in the orders table. I have to look in the orders items table. I also have to look in the products table, right? So if I'm making changes to those, I have to prevent access or lock all three of those tables. Does that make sense? In fact, as it turns out, I have to lock the entire table. So I have to prevent the user from touching any of those three tables, any row in those three tables. With me?
Yep.
Okay. So locking is something we've not necessarily talked about a lot, but it is a big impact and it's a big performance bottleneck oftentimes when you're working with relational databases, that locking that has to happen. So when you want to make things fast, you're going to run into that locking problem. The nice thing with the way that the most things work with document databases especially is oftentimes I don't have to lock any more than the document I'm working with. So if I want to update a document, I don't have to lock all of the other things. I just have to lock that one as I'm changing it. Does that make sense? So the scope of my lock is much lower. You can think of it being like just locking a single row instead of locking an entire table, but it's also you're just locking one table instead of 5 or 3, as it may be. Okay. Also, once we're pulling in these foreign keys to put the data back together, because the users want to see it back together. They don't want to see it as order items, right? They want to see it as orders. We have to join that data back together to allow the users to view it. Does that make sense? So
yeah.
All three of those are fallouts from using foreign keys, right? So if I didn't use foreign keys, then I can avoid some synchronization. I can avoid locking multiple tables, and I can also avoid a lot of joins. And so all of that put together, I can have much more performance, especially if I want to have multiple database servers if I don't use foreign keys. Because foreign keys actually tend to make things slow. Same thing with auto increment. Auto increment tends to make things slow. So those are problems with the way that we normally build databases with relational databases. But both of those things, as you'll notice, right, are very common things to do, right? Auto increment and foreign keys, right? Those are both things that you've done in every project that we've built, right? So those are places that people tend to, that's one of those things where, once you get used to this, you maybe have to come back to your, you start thinking about how you build your even building relational database and think, well, how can I do this without auto increment, and how can I do this without foreign keys, right? So a third problem that occurs with relational databases is that they don't allow for nested documents and arrays, and that's because of that requirement that rows need to have the same length. Every row needs to have the same length. So because of that, we can't nest things like documents and arrays typically. So that makes it, because we can't do that, because we start having to split things across different tables like orders and order items or blogs and blog tags, it can be also then hard to then take that data and go back and forth and translate between the world of objects and the world of tables. because our tables don't look like the objects we want to have. Right? So I want to have orders. I don't really want, the user doesn't care about this idea of order items. It's an artificial thing I've created. Same thing with blog tags. It doesn't really exist from the user's perspective. So we have to do a lot of difficult mapping between the data that we want to have and the data that we want to have on the front end versus the data that's on the back end. So that mapping is a big overhead. Also, connecting, because we don't have those nested documents or arrays, connecting related data often introduce a lot of complicated joins, whether it be left joins, right joins, inner joins. It adds a lot of complexity to have to add in those joins. Got it?
Yep.
So, if we could just nest documents, we can get away with fewer joins. Not saying that there is a way to do joins in Mongo, and sometimes you need to do that. But it's one of those things that, if you can avoid, then do. So because we're dealing with that, data, somehow we need to take our database data and we need to map it to objects. We also have to take our database operations anytime we want to do something to the data or read data or insert data, update, delete data. We have to map those operations, those actions that we want to perform to SQL commands. And that can be a problem in of itself, right? Because we have to basically translate it from the language that we're writing into a completely another language, right? I have to write my SQL statement in SQL, right? So somehow I have to translate the code that I'm writing in C# or Java or JavaScript into SQL. So we've used Connects to help us with that translation process, but we have to make that translation process happen because our database doesn't speak. Our MySQL database does not speak JavaScript, right? It speaks SQL. So with that being said, we end up creating a lot of classes just to be able to map between the world of databases and the world of application data. It's not unusual. I think, Ben, you can speak to this. How many different classes did we have to create for a data model just last semester when we were doing C# and NAD framework? How many extra classes do you remember having to write just for that?
Sorry, I can remember what my push to talk button was. I think it was a class for every single table, wasn't it?
It was, plus some additional ones, right?
Yeah, for whenever you'd have to, I think any of your tables you joined, wouldn't you have to create a class for those?
Well, not the join, but for the database itself. You remember we had that
Oh, yeah.
EF entity, the context class, the DB context subclass.
Mm-hmm.
So if I had, 4 tables, I needed at least create 5 classes. So that, part of that being it's in a type safe environment, but generally speaking, we end up creating a lot more classes just to do that translation. In fact, because the translation is so complicated, right, we brought in Entity Framework, and Entity Framework has its own set of classes, right? So we may have written 5 classes ourselves, but we're also dealing with 20 classes that somebody else has built just to do that translation, right? And I think there were a number of students that had, more than 5. I know that some of the students had, 20 classes in their model folder to deal with all that complexity, right? So if we were just able to nest data and just nest documents and arrays as subdocuments and subarrays and things like that, then we don't have to write a lot of those classes. So we don't have to write a lot of that translation logic because our data is, closer to our data in the database is closer to what it actually is in the application. Does that make sense?
Yeah, the more I hear about this, the more I think that the only reason we're using SQL is just because it's a legacy system and businesses
Right.
demand it. They haven't updated yet, and
Right.
they could, but they won't. So we're going to learn it.
Yeah.
And we
Yeah.
learn it better way.
That you are exactly right. It's the reason that we're using relational databases is because a lot of companies are using them. And that's what industry has told us, and that's what still is largely what I see as if I look for job postings, they still largely say SQL, but the reality is that SQL just doesn't fit modern applications very well. So I suspect at some point that will shift. It just hasn't shifted yet. So I don't know when that will happen, but I would, advise you, hey, I want you to know about this so that it's something you can suggest to, your employer, especially if you're building something new, right? Not building something that's already existing. Like, well, maybe just start with this and don't start with a relational database. So one of the things that a lot of times comes up is there's this idea of an object relational mapper, ORM, and that's what Entity Framework is that we were talking about just a bit ago. That's what we used last year with C#. But there's also, I think, SQLize is a Node module that is like an ORM as well for Node. But ORMs largely their whole goal is to make to kind of take that mapping between objects and relational databases kind of out of your hand and write a lot more of that code for you. So they kind of sit as a layer between your database and your code. So the idea is to make that translation easier. And well, why do we need those? Because the translation is just so freaking hard. So that's why we end up with adding another layer in there just to try and make it easier. So the idea with an ORM is it maps your methods and your objects that you're used to working with in object-oriented programming onto database data and operations, so that you don't really have to write SQL. It kind of writes the SQL for you. However, one of the key problems with dealing with an ORM, and I would mention briefly SQLize is one of those, but Connects, the one we're using, is not an ORM. It's what we call a query builder. So it doesn't have some of these problems, and that's part of why it was selected. But if you're dealing with an actual ORM, they tend to obscure problems with your generated SQL because you're not writing the SQL. You're very far separated from it. So they can hide a lot of the performance problems and prevent a lot of optimizations because you can't get in directly and mess with the SQL, or oftentimes see that's, what is it doing that's maybe doing something stupid that it doesn't need to do, or maybe it doesn't, support the full language that your database supports, right? Because it only supports what standard SQL is. So there can be a lot of things there where maybe you can't do it with the ORM, or can't do it easily with the ORM, or do it efficiently with an ORM because it doesn't fully understand your flavor of SQL that you're working with. So part of the theory with ORMs was that they generally make it easier to migrate your application from one DBMS to another. So if I decide I want to use Postgres or MySQL or Oracle or SQL Server tomorrow, in theory I can swap that out much easier. But one of the things that people find as they've built we worked on these ORMs, oftentimes they find, well, yes, okay, it may be easier to swap DBMSs, migrating from one DBMS to another, one ORM to another, is now much harder, because your ORM actually tends to integrate and put its tendrils into your code a lot more deeply than even the database does. So they actually tend to be more of a problem in a lot of ways. So that's one of those things that's been promoted, and a lot of companies have adopted to try and deal with the problems of relating to relational databases. But in my experience, they've also introduced a lot of problems. So I would consider them, ORMs as one of those things where, they're not necessarily, there actually can be a problem with working with relational databases. So one thing I would point out, though, ORMs are not necessarily strictly confined to relational databases. So there actually is an ORM or two out there for Mongo. It's called they're Mongoose and Bison are both ORMs for Mongo. So those exist, and I kind of vaguely understand why they're there, but I also look at them and I go like, well, if we're going to switch to a NoSQL database, why do we need to keep an ORM around? Right? So what we're going to do, as we work with Mongo, we won't be using an ORM. We're going to interface directly with it. And I know that the book that we picked out, I think that book covers Mongoose instead of covering MongoDB directly. If I remember right, the way that one's written. So that's, another kind of reason we've gone a different way. So it's worth noting some databases, including MySQL and SQL Server, do support XML and JSON data types. So if I remember right, specifically, SQL Server does support columns that are type XML, but you can't have type JSON. They don't have support for that. And MySQL, you can make a column that is a JSON data type, but they don't have I don't think, an XML data type. So the theory is, that if a lot of people say like, well, okay, so I can add JSON, right? I can add a JSON column to my database, to my MySQL database, and now I kind of have the benefits of MySQL, right? Or benefits of that, right? Of a NoSQL database. If I just have a column of data type JSON, right? But that doesn't alleviate any of your problems with foreign keys or auto increment and some of those other things. So if you do make it type JSON, well, okay, so now you can nest objects and arrays similarly with XML. But one of the things that happens is querying that data is actually hard and sometimes impossible. Because the basic SQL syntax doesn't allow for querying oftentimes inside of those columns. Does that make sense?
Yeah.
So if I have an object in my users table, I call it user data. Well, what if I want to reference the third object, the name property of the third address in their address book, in their billing addresses? Well, how do I represent that in SQL? SQL doesn't necessarily have a way to write that. So it actually requires extensions to the SQL syntax to be able to deal with those JSON or XML documents. And those syntax extensions are very much vendor specific. So now you've lost all the benefits of like your SQL being agnostic, right? So if I'm using that, if I use those JSON bits, the other thing is oftentimes they're not most databases are not optimized for that. You can have JSON, you can have XML columns, but they're not optimized for making that efficient. Most databases are. And for one part of that is that you usually can't, the way the indexes are defined, you usually can't index inside of a JSON or an XML document. A lot of databases, they might support that, but they don't necessarily support indexes on it. Does that make sense?
Yeah.
Or they might not have specialized the syntax extensions for that. So that means that you then have to do the filtering in your application instead of doing it in your database. Which can mean things like if I want to say, let's make tags just a JSON column. Well, if there's not proper support there, well, then I have to load up all the blogs and then do the filtering by tag in my application, in my JSON, in my JavaScript code. That's going to be really slow, right? Because I have to load all of the blog articles. Does that make sense?
Yeah.
So that's one thing that's kind of out there, and I think a lot of people are having faith in these JSON column data types that they're going to replace. Say, okay, well, we can still use MySQL and SQL Server now because we have these. Those mean that we don't have to migrate, but I don't think that's really going to pan out because they don't really support. It's not their primary user, if that makes sense. Like, this is an additional back burner feature, and it's clear that a lot of companies have not prioritized XML or JSON, columns in the way they're building their database. Does that make sense? So you might be able to do that with Postgres and MySQL and SQL Server, but it's not their primary bread and butter. So that means it's, you're kind of suffering from that versus, you're not going to get priority in terms of features and stuff. Whereas, that's the bread and butter for MongoDB. So they're going to support it and they're going to try and make it efficient. So what that means, looking at those issues, I would say that relational databases, and I already kind of said this, are not optimized for today's applications. Relational databases, with all of those implementations, all those different bottlenecks and different issues beyond what we've talked about, generally can't handle more than a few thousand concurrent users. It's really a struggle with a relational database to handle more than 100 users on your website at the same time. And I'm not kidding. It is really hard to make that work because you have to know about all these different bottlenecks and deal with them. And know that, okay, foreign keys are a problem and auto increments a problem, and I need to have multiple servers, and how do I deal with having server synchronization and backups and all of that becomes, there's a point where, that's a problem. And relational databases overall are not optimized for distributed database servers. Because of all the synchronization overhead, even beyond what we've talked about, there are usually some major bottlenecks in there that up to the point that it limits you to 3 servers at most. It's hard to go above that number with relational databases. Does that follow?
Yeah.
So that means it's hard to have, like, hey, if I'm going to build Netflix, right? There's no way I'm going to build that with a relational database. It's impossible, right? Or if I'm going to build Facebook, there's no way I can build that with relational databases, because the synchronization and the number of users I need to have on at the same time is just way and above what they were ever designed to handle. And so, and they're not optimized for unstructured nested data. Many of those don't support it because they don't necessarily even have JSON columns or not full support for those. But that's kind of a common thing we want to do. So to kind of, sum up what we've talked about, we've talked about what some of the issues are with, relational databases. But if we kind of look at what we looked into, it's like, well, okay, so auto increment is bad. We need to watch how we do our primary keys. Foreign keys are a problem, and joins are a problem, which is kind of weird. It's like, wait, those are all three main things that we do with relational databases, right? Auto increment, foreign keys, and joins, right?
Yep.
Like those are kind of fundamental pieces, but you're telling me those are problems? Well, they are. They're problems for scaling your database up to deal with lots of users and lots of servers. So this is why a whole nother database module is really called for, is because those core things are such a problem. So talking about terminology, when we're dealing with MySQL and relational databases in general, we talk about schemas, we talk about tables, we talk about rows, and we also talk about fields/cells. Fields and cells, kind of the same thing. But when we're talking about a field, we just mean basically a single piece of data. And so with relational databases, that is a intersection between a row and a column. So we call it a cell, sometimes. With Mongo, opposed to that, we talk about schemas. We still talk about schemas. Kind of means the same thing that you would think of. Schema kind of defines your the way your data is structured, the way your database is structured, and what things it has, and what fields are in there. But it's a little bit more loose. The schema is a lot more loosely defined when you're working with MongoDB than it is with MySQL. It's a lot less strict. To the point that, remember, as we've been building these databases, we've created this long script just to set up the database, right? To create all the tables and put data in them.
Yeah.
Define the foreign keys, define the indexes, all that. You don't need to write a SQL. You don't need to write a schema script with MongoDB.
It just gets better and better.
You don't need to write that script. All you need is your data. So you don't actually need to define a schema per se formally. I'm still going to ask you to make an ERD diagram and stick to it, but you don't actually have to have a script to define your schema with Mongo. So we talk about this idea of a schema, which is still the database structure in the similar syntax. It's just more loosely defined. The more abstract, we've got this idea of a collection. So a collection contains an array or a list of documents. So you can think of a collection as kind of a named array, or you can think of it like a table. A collection is very similar to a table. That's usually kind of the analogy that people draw, is they'll take their tables and kind of turn them into collections. So within those collections, we have documents. Those documents must be JSON objects. They must still have a primary key, but they're more maybe loosely defined than your rows, but they're analogous. So analogous, kind of like a table has rows, a collection has documents. Okay? And within those documents, we have fields, just like our rows have fields. And those fields are modeled, though, like properties in JSON or JavaScript. Got it? Because they're properties of objects. They're not cells in a table. Okay, but we can still refer to them as fields because they're singular. They're still pieces of data. But they don't have to be scalar like fields don't have to be scalar like they do over here. So in SQL, we have schemas that have to be strictly defined at the beginning, at the get-go, And generally, our schema needs to account for future growth over the next 10 to 20 years. No joke, because that's how long the system is likely going to be around, right? It's very likely that system will live for 10 or 20 years. So you need to, if you're defining a schema for it, you really need to think that far ahead, which is hard, right? It's really hard to think what the world's going to look like 20 years from now.
Yeah.
But you have to really think about that when you're defining your database. You can change the schema, but in general, those schemas become difficult and slow to change. So what I mean by that, for instance, first of all, it requires a lot of communication between your team, because if I add a column, it's probably going to break a lot of pieces of code. If I change any part of that schema, it's probably going to affect a lot of things, right? So the other thing that happens, let's say I take my users table or my orders table. Say I take my orders table, I want to add just one column, right? Now remember from our previous example, that orders table usually has a lot of orders in it. So let's say I have an orders table and it's got 1 million rows in it, right? So to add one column, and remember this is down to the idea that every row needs to have the same length. If I change the length of a row, now I've got a problem, right? Now I've got a problem. So if I just add a column, that makes the row wider, right? So all of my offsets are wrong, which means that in order to add a single column to a table, I have to completely rebuild that table. It's tantamount to taking a backup of the database, backup that table, and then inserting every row back in. Do you follow?
Yeah.
So just by, if I take a table of 1 million orders and I say, let's just add one column, doesn't actually matter how wide that column is. Let's say, it's even just a bit to say it's been paid, or that they bought it on sale. Just a tiny Boolean. That could easily take an hour. Just add that one column, if not more, depending on how good your hardware is. And will take longer if you have more servers, because now all the servers have to do it. You follow with me?
Yeah.
And not only that hour or so or longer, while it's changing the orders table, guess what happens for your users? They can't use your website because it's changing the orders table. So while it's changing the orders table, they can't query that orders table at all. They can't do a select statement on it. They can't insert data. They can't update data. That's stuck until it's finished. Does that make sense?
Yeah.
That's part of what I mean by making a schema change is really hard and really slow, because adding or removing a column can easily take hours. Can easily be an hour just to do that. That seems like such a small thing, and it seems like, if you do that locally on your computer, it's going to be very quick because you don't have a lot of data. But when you scale that up to lots of rows, it becomes a problem. Also, with anytime we're talking about the schema and talking about the tables, those tables have to have the exact same columns. And each row in the table has to have the exact same columns and data types, and that goes back to the idea that every row needs to have the same length in bytes. And as it turns out, I'm sure you've seen this, a lot of database errors when you're trying to insert data or work with the database where the name of the things have changed or the data type of the things have changed, right? If you rename something in the database, that usually breaks your application.
Yeah.
and usually breaks it pretty majorly, right? So a lot of applications, most applications that people build with relational databases are not really built to account for that. They're generally not built to deal with those problems. So if you change the schema, it's very likely that the application is going to break. If it's at all different, if the schema is at all different than the application expect, the application probably won't work at all. Oftentimes, or will be majorly hampered, and there's a major features that you can't access because the schema is different. And that could be an issue, especially for things like test environments, right? So you got to make sure that your test environment has the same schema as your development environment and your production environment, right? It has the right schema to go with that version of the software. So those are, that's one of the things that you run into. On the contrary, with MongoDB, and I mentioned this on the previous slide, we actually never have to define the schema. Never has to be defined. There doesn't have to be any sort of formal documentation in place where you define these are the collections, and these collections have these fields. They just have the fields that they have, and you just have the collections that you have. Collections and fields are just added as you need them. So if I put in my code that's inserts a new record into a collection that doesn't exist yet, it just creates that collection. If I want to put in an object and it has a field that we've never seen before, okay, that document has that field. Does that follow?
Yep.
So if I want to change the schema, because it's never defined, I just kind of change it. And then I let, documents in the collection, well, they can have, they don't all have to follow our quote unquote schema. So they can have, your documents within your collection can have different fields, and they can have different data types. So it might be that, you originally built your e-commerce application, and you said, well, I'm just going to have a flag to say whether or not I'm just going to have a flag to say yes or no, the order was paid for, right? So originally you just had it as yes or no. And later you came back and you said, okay, well, let's enhance that. Not yes or no, let's put the date, right? So I'll put in my payment date instead of a yes or no flag. Well, because things don't have to have the same columns, you can still have that old data says yes or no, and the new data says the date and time. Does that make sense?
Yeah.
So you can have old data that still follows basically the schema that it was at the time, and new data that follows the new schema. That's perfectly valid, and that's a normal thing to do. Because it's like, well, why I can't go back to that old data and fill in the time that it was paid? I don't know, right? Because I didn't track that. So I can't go back and generate that data. So it's just going to have to stay with that old schema. So that's, but that's okay. That's fine. And then when I come down later and I say, well, just the payment date is not enough. I need to know, not just the date it was paid, but I need to know what credit card number was used, what the CCV code is and the expiration date, and what company processed it. Did I run that through Stripe or PayPal or whatever? I can now add that in there. And again, I don't have to change the older data that's in the older schema. I just have the new data following a new schema. Does that make sense?
Yep.
So that's a very common thing that we do, is that, data will evolve over time, and we don't need to make all the data with MongoDB or NoSQL databases in general. You don't need to make the old data conform to the new spec. That's not a requirement. And that means that you don't have to, because you don't have to do that, you don't have to spend several hours adding a column to a table. You just say, okay, here's a new document that has that field, right? So there's no loss there in time when you change the schema. If you do want to get the old stuff, old documents up to the new schema, and there's a way to translate that, well, then you just write a script to go do that. And you write a script, and that then runs through the data. You run it once or twice or weekly or whatever you need to do, and make those automated changes. If you can do that, but obviously sometimes you can't. So what I'm trying to say with that. So let's say the through that process, the whole time that name of that column was payment. So payment first, it was yes or no. And then payment in some documents is a timestamp. And then payments for the newer documents, it's an object. That's okay. It can have the same name, but a different data type. Cool?
Yep.
Yeah.
So that means that things like, it doesn't enforce, I don't say that the name has to be a string. And there's actually no way for me to say that. It doesn't enforce any sort of type checking on your fields. So that's something I have to implement in my application. I have to implement the checking for those data types. And that typically means using Joy, which we're already using, right? To check things. It just means you have to use Joy to check the data before you put it into the database. Problem solved. So given those kind of flexibilities and things that are already built in, typically, you still have to build around those. But typically people are smart about realizing, I'm going to have data that isn't necessarily the same. So it's much easier to ends up being much easier to handle changes to the schema because you're already aware that that's not enforced at the database side, that things could change. So it's usually a lot easier for us to build applications, and it almost happens accidentally that our applications usually work for data that doesn't conform to the schema. It's unusual for your application to crash with MongoDB if it doesn't agree with the schema, because in theory you've thought more deeply about it. Does that make sense?
Yeah.
Because it wasn't so strict in the first place, you're not relying on the database to be enforcing those. So generally people are smart, and they put in if statements and for loops where those things are possibly different. Which means that things work a lot better and a lot more stable. In terms of required fields, in MySQL, remember we could mark required columns with not null, and otherwise null would be allowed. With Mongo, again, not really having a schema, everything's optional. Every field is optional. So if we want to make a field required, that can't be checked on the database level. We have to do it on the application level. So that's back in where we're implementing things with Joy. Okay, well, then we just don't check it twice, because that's actually what we were doing, right? We're checking that it's required on the database level and in our application. So that's, okay, that's fine. Well, we already had to do that in the application, so we'll do that in the application. So that's just something you have to be aware of. Like, you can't just rely on your database to check if the field's required. You have to implement that yourself. But we should be implementing that anyway, so no big deal. So as long as we've got server-side validation coming with Joy, most of that stuff just kind of we've taken care of it. Working with primary keys, typically we've created those as auto increment. You can actually do it 3 different ways. With MySQL, the primary key could be auto increment. It could be a composite key. We've done that with a lot of our bridge tables, is make them composite keys. Or they can actually be something called a UUID. It's a universal unique identifier, which actually is very similar in structure to how the object IDs work in MongoDB. So just so you know, there is kind of a system. You can use UUIDs to get some of those benefits in MySQL. Most SQL databases have a way to do this instead, and a lot of people have started to migrate away from auto increment and to use GUIDs or UUIDs instead, because of the benefits we talked about, between not being able to guess it, them being more random, being able to do things offline. But basically, the idea is that you randomly generate a number that's unlikely to be occur again. Unlikely for there to be collisions. There can still be two things can come up with the same ID, but it's very unlikely that would happen. And then you just deal with it when it does. So the ways that those are stored, you can look at the documentation in MySQL if you're curious about how that works. There is some methods to work with UUIDs. There actually is no UUID column type. Microsoft SQL Server does have a GUID column type, so you can specify that as the column type. That doesn't exist on MySQL. So the way that you can store it is actually one of three ways. You can store it as an unsigned bin int, car 36, or var binary 16. You kind of look at, you look into the documentation to see what that is, but there's different ways to store the data. But basically, here's an example down at the bottom of what those would look like. So it's a bunch of different sections you can kind of see with dashes in between. So that's what that looks like. With MongoDB, they have to be object IDs. You don't get an option. Your primary key has to be an object ID, and it has to have the name _ID. Cool?
Yep.
That is your only option. There's no composite keys. There's no auto increment. It has to be an object ID. So an object ID looks like what's over on the right. So it's very similar in concept to how a UUID works. There's differences in how they're generated, but the idea underlying is very similar. But it is a different format than UUID. Okay. Foreign keys. If we wanted to add foreign keys in MySQL, we had to do two things. We first had to add a column to store the primary key of another table. So we did that with things like the author ID, the product ID, the customer ID, adding those kind of columns to there to store it. And then we had to add the foreign key constraint to prevent the column from becoming invalid. So those were the kind of two steps that you did. You had to add the column and the foreign key, right? So with MongoDB, if I'm setting up a foreign key, all I'm going to do is just add a field. I'm going to add a field to the document or object to store the primary key of another document. There's no way in MongoDB to enforce the validity of that foreign key. And it's a good thing, because it means we won't have all that extra overhead that comes with enforcing that validity, including synchronizing all of our servers anytime you make a change, and having to keep our servers in sync. That's then not a requirement. So database, you can have a bunch of database servers in MongoDB, but it may be that each of those servers don't necessarily have a full picture of the database. That's okay. If you have multiple instances of MySQL, each of those instances have to have the exact same database at all times. That's not true with Mongo. So I might have my server in the US and China, and they might slightly disagree about what the current data is. That's okay. Eventually they'll sync up over time, but they don't have to stay constantly in sync from the second to second. So that's actually a really good thing that it doesn't provide a way to synchronize those up, because it allows Mongo to actually be more performant, because it doesn't have to enforce those foreign keys. Oftentimes the other way to, instead of having a foreign key in the first place, oftentimes you can just nest the related document inside, like we did with orders and order items, and that can be a better solution in a lot of cases. It's not, the right solution in all cases, but a lot of times that's actually a better solution than having the foreign key in the first place, because if it's nested inside, you can never have an invalid foreign key. Does that make sense? If you don't have a foreign key, it can't become invalid. Got it?
Yep.
So working with unique constraints do actually exist on both sides, because as it turns out, they're a super valuable thing. Unique constraints are defined when we're working with MySQL. We define the unique constraints as part of our table schema. So we might say like the username is unique or the email address is unique. And those unique constraints can include a group of one or more columns, which must be unique. The group must be unique for each row of the table. And then at any given time, all rows in the table must satisfy that constraint. It's not allowed for there to ever be a time where the rows in the table don't satisfy the uniqueness constraints. Like if
I got a question about that. So
Yep.
you mentioned that with MySQL, everything's got to be up to date. Everything's got to be online. Database got to talk to each other.
Yeah.
If we're talking about a unique constraint, how is that possible with MongoDB? You might have one of the servers offline, and they try to register with the same email account by chance.
It would potentially allow it.
Oh, okay. So you just got to be more aware and disambiguate later on.
Yeah, you may have to come back and fix that later on. It does provide a way to try and do that. They do communicate with they do at least try to communicate with each other as you're putting stuff up. In fact, just one note on the kind of normal deployment of MongoDB. For you, you'll just be running one server on your laptop when you're testing it. It's usually the development setup. But when we deploy it in production, the way that they deploy it in production is usually with clusters of 3. So it's very rare that actually in production that you use one MongoDB instance by itself. And part of that is redundancy, but also scalability. So typically you might not, with Mongo, we wouldn't probably have one server we wouldn't have one server in the US and one server in China. We would have a cluster of 3 in the US and a cluster of 3 in China. So it's actually unusual and not recommended to just have like one server by itself. You usually have a cluster. That being said, yes, in theory it could become there is the possibility, and I don't know this for sure, that if that can happen or whatnot. But in theory, there is that possibility if some clusters are offline, that maybe your unique constraint could become violated. Cool. So you just have to deal with that after the fact. It's like, okay, 2 users have the same username. Now you have to figure it out.
Right, and it just wouldn't happen that often, because if you got that cluster, the chances that all 3 are offline at the same time, not that great.
Right. Well, it's more like, it's unlikely because you have 6 servers actually there. It's unlikely that all 6 would be offline. But the thing that could happen is, say the 3 in the US go offline, but the 3 in China are online. That could be a problem, and where that could occur. But as long as the databases are not too far out of sync, then it's not a big deal. Does that make sense?
Yeah, it's unlikely to happen. I see that.
Right. Because that can only happen as long as the databases are out of sync. So let's say if it takes them, an hour from when the user is registered to when it's synchronized across all 6 of those servers. Specifically, if it takes an hour for it to synchronize between the US and the Chinese servers, that hour is the only period of time where that can happen. Does that make sense?
Yes.
Because from that point, after that hour is expired, both sides, both clusters know about that user, so they can say, nope, that username is there. So it can happen. It doesn't happen all that often, if that makes sense. And there are some controls that you can specify when you're inserting records about, how many servers need to agree with that before you can treat it as accepted. So there are some things knobs you can turn. But while it can happen, is not all that frequent. So with MongoDB, we don't add it. We don't have that schema. What we do is we add indexes. Specifically, there's a flag when you add an index to a collection called unique. So you can mark that index as unique, and then that will enforce the uniqueness on that collection. So we add a unique index to it, and then we can say this one or more group of fields, these have to be unique for each document in the collection. And then all collections, in theory, should be satisfying that constraint all time, minus the synchronization time. Okay. So they do exist there, but yeah, there's a little bit you might have to worry about because of the sync stuff there. So working with indexes, if we're creating an index in MySQL, we define it as part of the table schema, typically, and they're used to speed up database operations where the columns in question are used in a where clause or a join clause. So if you have a where that's referencing, say, the name of a product, or a join that's referencing the product ID, things like that is where you would see the index used, is wheres and join. Okay. So with MongoDB, we can add indexes to a collection. Kind of makes sense because collections are kind of like tables. So we add it to the collection. And they speed up any find operations that filter data based on the index fields, or any other thing that we do, any operation that we do that filters data. So with MySQL, especially when you're dealing with small tables, those indexes can be kind of optional. On the other hand, when we're building MongoDB, those indexes are actually really, really vital to application performance. It is really important that you make sure that you add the right indexes. Where you might not necessarily see an obvious dip in application performance with MySQL if you don't have the right indexes, you're going to see an obvious dip if you don't have the right indexes with MongoDB. Cool?
Yep.
And the reason that is because basically the indexes make up for all the stuff that we all the good things that we've taken that have slowed down the application. Like the fact that the rows don't all have the same length, that they don't necessarily have the same structure, they don't have the same fields. That's where indexes basically make up for that. Got it?
Yep.
So if you don't have those indexes, your application will be slower with MongoDB than it is with MySQL. Hands down. So make sure as you're defining and thinking about how to store your data, it's really, 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 really important to think about the indexes, even more so. All right. So now we've kind of talked about some of the differences and why we're even talking about NoSQL database, why we're even talking about MongoDB, and some of the considerations that you need to make. Let's actually get some of the server and software installed and talk about how to do that. So the first thing we're going to look at is the MongoDB server software. You've already installed MySQL, the MySQL community server. What we're going to use here now is the MongoDB community server. So this is the freely available version of the MongoDB server. You can go through, I put a few links in here to information about it, the download page, and documentation. It runs on your local machine, basically very similar to how MySQL server works. And it's something that's free. It's freely available. You don't have to pay for a license to use this, so you can just get up and running with it. Okay. So if we go to the website, the place where you're going to find this, see, I'm on the main page. If you go through Start for Free, that actually directs you to something called Atlas, which we'll talk about in a minute. That's not actually where you go to download the MongoDB server. So don't get confused by that. This is not where we're going right now. Where you want to go is to go to the downloads. You'll see a few options. We want to get the community server. Okay, so you can grab that. There's a few different categories here. You'll notice there's cloud, there's on-premise, there's tools. So we're in on-premise and we're in the community server. The enterprise server is like the business, the commercial version. So we'll be using this version because it's free and it's all we need for testing. So MongoDB community server, we're going to get the latest version, which right now is 4.4.1. I'm going to go to current. And then I want to go Windows. You can either do MSI or zip. I would do definitely MSI. Okay, so let's go download. Okay, so you want to pull this down. This is going to include actually not just the server. This download actually also includes Compass and the shell. So there's actually more things in here than just the server. So this is definitely one you want to install. Okay. So now that I've downloaded it, I'm going to go ahead and hit next or run the installer.
We can't see your installer.
Oh, I will fix that. Change Windows. Sorry about that. Okay, you can see my installer now?
Yep.
Cool. So when it pops up, you'll see something like this. I'm going to hit next. I'm going to accept the license agreement. And then you have a few options. You can either pick complete, which is going to say let's install everything, or you could go through custom. If you look through custom, it'll give you a few options about what you want to install or not install. So you've got the server, you've got the client. This is the shell. You've got the router if you want to connect more than one MongoDB instance, and then some miscellaneous tools. So you could go through custom and pick and choose what you're going to do. What I would do here, though, is just go complete because we want everything. So we're going to hit complete, and we're going to say, yes, we do want to install MongoDB as a service. That way it should start up every time we boot our computer. Similar to we talked about with MySQL, if it doesn't start up, then just go to services.msc and start it. But it should, by default, this way, start anytime your computer starts. So we're going to install a service and run it as a network service. So we can leave all that as is. And then there's this next one that says install MongoDB Compass. If you, for whatever reason, don't want Compass, which you do want Compass, you can just uncheck this box and it won't install Compass with its install. But we do want Compass, so please leave that checked. That's how this Compass is basically our equivalent to MySQL Workbench. That's how we're going to work with the database. So we want to install Compass. Ready to install, and go ahead and hit install. Yes. Setup must update files or services that cannot be updated while the system is running. If you choose to continue, a reboot will be required to complete the setup. Okay. Because I already have it installed. That's why it's telling me that. So assuming you run this through with the complete and Compass install, this will actually give you everything you need to work with MongoDB. There's not a separate install then you have to go do. It's just this one. And obviously you'll want to install MongoDB on all the computers that you're using for class. So if you've got a desktop you're using at home and a laptop you're using for on campus, make sure you get this installed on both of those devices. Is anybody having issues with getting MongoDB installed as of yet?
Not yet.
Okay.
Wow, school internet is trash.
It's telling me I can restart now, or I can restart later. Should I just restart it later when my computer goes off?
I would restart later, yeah. I would tell it to restart later, because otherwise it's going to kick you out of Discord. But as you see, it's pretty simple because I just basically picked all the default options. It's nothing fancy I had to configure. So click Finish to exit Setup Wizard. You must restart changes to make take effect. I'm going to say no. All right. So now that it's finished, it's actually gone into Compass. So we're going to say start using Compass. And the way you get back here, if you do close this, you just go to your start menu and type in Compass. Mongo. Okay, there it is. MongoDB Compass Community. That's the one. So you can get back in here. Okay. So if you want to connect to a server, we're now running one locally. All you need to type in is localhost 27017. That's the default port, or you can just click on it in the left if it's in your recent. It may be suggesting it for you as well. I think because I've used this previously, it's not. But if you want to type in the database URL directly, the protocol is going to be MongoDB. If I can spell MongoDB and :// and then it would be localhost is the name of our server, port number 27017. So that's what you want to type in to connect to your local server. Okay. So I'm going to go ahead and hit connect. And it shows me locally having 3 databases already. There's the admin, there's the config, and there's the local. These 3 exist with just a basic install. Don't touch them. These admin, config, and local databases, you don't do anything with them. They're needed for MongoDB to do its thing. Cool?
Got it.
So if you want to put any data in here, you need to create a new database. Do you think any idea where I'm going to go to create a new database?
Button that says create database.
Probably, yes. So let's go create a database. And it's worth noting, actually, with Mongo, if your code uses a database that doesn't exist, Mongo will automatically create it for you. So as soon as you start adding documents to a database, if that database doesn't exist, it will just go ahead and create the database for you. So that's worth noting. So if you misspell, if you say misspell the database name, you're going to find that it went ahead and created the database for you, for instance, is what that means. So my database name here, maybe let's just call it Cowboy Boots. Okay. And there's a collection name here because what it'll do is it'll initially create a collection, a table at the same time. So I'm going to call that collection products. So I'm going to create my database as database name Cowboy Boots, collection name is products, and now you can see it popping over here, right? So what you're seeing over here is the databases, and then underneath that, you see I can expand and get to my collections. Got it?
Yeah.
So I've got products in here. I might want to add another collection. I can do that through the little button here, say create collection. So we've got products. We're probably also going to have users. So let's go ahead and add a users collection as well. So that's all I need to do to create databases and collections using Mongo. And you'll notice in there, have I specified what columns or what fields any of these collections have?
Nope.
I haven't, right? So it's actually super easy because I don't need to specify those things. I'm just like, well, I need to have users and I need to have products. So let's just make a place to put them. So there's really not much setup you have to do there. You just give it a name. The one thing you do have to remember is then, as we said, indexes are really important. So you do need to go and create some indexes on those collections. So let's say we're working with products, right? What might be, I can go over to, I'm in documents is where it starts. I'm going to go over to the indexes tab. So what might be some things we want to index when it goes to products?
Product name.
Product name. Okay. So let's say we create an index for the product name. Okay. So I need to give the index a name. This is not the name of the column it's indexing. But oftentimes I just use the name of the column here. So I'm going to just say name and select a field by name. It doesn't give me anything because we don't have any documents yet. So I'm just going to type it in. Name. And we're going to say it's ascending order. Okay. So name, ascending order. Now, before you do create index, let's look at options. Options is kind of hidden here. There's a few options that you can pick. And the one we're interested in is making the name unique. Okay. So we want to make the name unique. All we have to do is check that box. See that? Create unique index. If you forget to check that box, the only way to come back here and fix that is you have to delete the index and create a new one. Okay?
Yep.
So we're going to create a unique index. You can click the I. It'll give you an article about what that does and how that works. So you can find more information that way. So we're going to create a unique index there. Call it name. Be on the name column. Now it's added in here. And you'll actually notice if you pay attention, we already had an underscore ID column, ID index, because that always gets added to your collections. Your collections will always have an index on the primary key, on the underscore ID column. And that will always be unique because remember, primary keys have to be unique, not null, and not modifiable. That still applies. Cool.
Yep.
Okay. So we've got an ID, we've got a name. What are other things that users might use to look for products in our store?
Price.
Price. Okay. So let's create an index on the price. Okay. So maybe an index there on price. Make that ascending. Typically, I just make things ascending. The order of that only really matters if you're indexing more than one column at once. So usually you can just make it ascending most of the time. Okay, so we can index that, and that will then speed up any queries where they want to filter by a range of prices. So that will make those things fast. And anything where they want to look for a product by name, well, that will work. Oftentimes, users want to look up products by, for instance, like the price. Or it's not the price, the category. So I could add an index for that as well. So I might say category, field name is category, ascending, create the index. So right there, okay, I've created some indexes. So you can see the actual index creation is super easy, right? It's really not that hard. It's just a matter of figuring out how is the user going to use your database, right? Now, inherently with this, I need to then make sure that when I name my fields, name my columns, I name them those names, right? Because I said it's indexing category, name, and price. If I call this product category and product name and product price, it's not going to use these indexes. Got it?
Yep.
So I've presumed to know the name of the column before it's actually there, basically. Okay. Yeah, and you'll notice that, how many of those are unique?
2.
Okay, 2, the primary key and the name. So, you're going to have some unique indexes pretty normally. You'll still have plenty. There still sometimes collections that don't have a unique index, but you should have relatively few being unique compared to the number that you have. So, things you can see in here. Yep.
Getting this red error, you must select a field name and type. I've done one already, but no matter what I do, it won't let me put another one. You must select a field name and type.
Yeah. Well, let me go to the users and we'll add one there. So for instance, let me go on username. When you type that in, you see how it says create index username? If I just click off of it, you see it goes away. I have to type it in and click that button. So you have to say create username, and then it's there.
Oh, all right. Not so intuitive, but I got it now.
Yeah. So that's all that's what you have to click into there. You have to type it in. Okay. So username, we want to mark that one as unique because our users should have a unique username. We can do the same thing with like the email and say that the email has to be unique. And I did the same thing there. Email. Boop. Create index. Cool. Okay, so we've got some indexes on both of those tables. Any questions so far on that index setup?
Nope.
So, the big thing to do there is just to think about what you're going to do with the application. How is your user actually going to use it, and that will kind of dictate what kind of indexes, what columns you index. So I've got users and products. Let's say we want to add some products. So I can go back up to products, and let's add some data. So there's an add data button. I'm going to say insert document. You can either do import file, which is if you have like a JSON file that you've written in your text editor, you can bring it in that way, or you can bring in a CSV file. But here I'm just going to type in, I'm going to do insert document and just create it here. So the way you have to write this, you have to write it as actually a JSON document. So I'm going to put it in dupe. And so let's see. So I want to create a product, and so we've got a name for that product. We said we're going to have. And so maybe this is, I've got some red boots. And, I need to use double quotes for this. It won't let you do a single quotes. So double quotes, red boots, maybe a price. I think I did 160 in the example, right? So maybe price 160. Category boots. So I can write out like a JSON document that way. Everybody see that?
Yeah.
And then you just say insert. Okay. So it's going to put it in there, and you can see now that there's a document, and it's gone ahead and created an object ID for it. Cool. There's a few different ways to look at that data. So you'll see there's a view kind of toolbar here. So right now it's in this sort of list view, which appears this way. If you go to the curly braces, you'll see it appearing in JSON, basically as it's stored. The other one you can click is this tabular view, and that'll kind of make it look like almost as it does in a relational database. You see that? So you can look at it here in Compass almost as if it was a table in many ways. Now, once you get to nested documents and arrays, this will not be as convenient. You'll probably want to go back to this view, but you can see that you have that option. Cool. Questions?
Nope.
Okay. Let's say I put in another 2 documents in here. So I'm going to say insert document, and I believe if I put it in an array, I can actually do 2 at once. So I'm going to put curly braces, and the name of the product is big boots. Price is 200, and the category is also boots. And just to demonstrate that I can add more things, I'm going to add a size property to this one and say it's big. Size is big. In fact, I could come back to the other one and say, well, this one's available in multiple sizes. So maybe I could say, well, this one is, go edit it. I'm going to add a column, add field. And so we're going to say size. And this over here, I want to be, why is this? Oh, I need to go over here and change it. So it's an array, and it's small, and medium, and large. Update. There we go. So now this one has the sizes being an array, right? It's got multiple sizes available. And I think you can start to see how this, the system becomes very flexible to start adding things like that. It's like, oh, I want to support multiple sizes. Done. Right? I didn't have to go drastically change the, and add another table, another collection to do that. I just added the data. So I can do things like that. And now if I want to, let me add one more so I have something that's a different category. So maybe I add one more here, and so name is gold eagle buckle. Price is 50, and the category is buckle. Okay. So we've got 3 products in here. Sometimes you'll want to, as you start having more data in there, you may want to start kind of searching that data. So you'll notice there's kind of a search bar up here. Does everybody see that?
Yeah.
And the way you specify your searches uses a special syntax, which you'll actually get really familiar with. It uses a filter object, which is why it's kind of saying there. And the way I write that filter is something like this. So I'm going to say, and kind of think it almost equivalent to a where clause. So let's say I want to look for category. So category colon, I want to look for where the category is boots, and hit find. If I spell it correctly. Find. There we go. So then I'm filtering down to the just that category. Or I could say, well, I want the product is price 200. So I could say, well, the price is 200. Find. So I can filter down the data or search the data just from that bar. Cool.
Yep.
You just have to use that syntax to search. Okay. So we looked at how to do those pieces. Another important button in here, you see there's a button for export collection. Everybody see that?
Yep.
It's right next to add data. I can click export collection. It says you can export with filters. So if I wanted to not export all the data, I could do like a category filter or like that. But I'm going to say let's export the full one. And then we'll go to select fields. I want to export everything. And then we're going to say select output. So let's export as JSON. And maybe I go to export this to base unit 4 examples, and maybe we call this folder cowboy boots MongoDB. Export. Kind of similar to what we've done previously. I'm going to just toss this into a data folder, filtering data, and let's call this my products. So it's going to get saved to products.json. Okay, export. All right, so let's go look at that file that it exported. It's actually pretty easy. So projects. So edit that. There we go. So there's what it exported as. So you can see by that kind of looking at the curly brace here, it exported it as JSON, right? So you can take your data, and if you need to back it up or save it so I can get it, that's all you have to do is you just export your data. Cool.
Sweet.
So if you do need to take a backup for any reason, transfer it from one computer to another, that's all you have to do is just export the data and then import it on the other computer, and set up the indexes. So rather than having a schema, this is kind of, you have your data, right? So that becomes a lot easier to kind of get up and running oftentimes. Okay. So we looked at getting the server installed. We looked a bit about how to use Compass. One thing I want to mention is that so community server runs on your computer, as I mentioned. So if you're, say, you're doing work on two machines, or you're trying to use the same data in production, you're going to have to transfer that data, right? There is another option for hosting your database. So you don't, like, hosting it on a server is not the only way to do this. On a local server, you can use something called Atlas, which MongoDB provides, which is sort of a cloud-hosted version of the server. And it's actually a really great fit for connecting with your live version of the website. So, when you go to deploy this to Heroku, basically you can get a URL that's going to be your connection string, your details to connect to your Atlas cluster. And you just put that into your database config, and now you've got your application connected to that Atlas cluster and using the database online. I would strongly encourage you to do that for being the way that you deploy applications to Heroku with Mongo. So that's how I want you to do your deploys there, is have it connected to Atlas. You can also actually use it not just for the production version, but you can use it for testing, as a way to eliminate the need to migrate your collections and indexes from one development machine to another. So if instead of doing all your database setup on your computer, if you set it up in Atlas, you can actually get to that from anywhere on the internet. So I would, especially if you're doing two separate computers, I would recommend doing that in Atlas. But I also actually ask you to set it up in Atlas because it's going to make it easier for me to test your application, as then I can easily get to your database as well. Cool.
Yep.
So that's one thing I would really ask for you to do as far as setting up your database and hosting it. You can kind of play around with it locally, but it helps me to be able to test it if you do it through Atlas in fact. So Atlas provides a free tier to it. When you go in here, you can have it hosted in a few different ways. So you can have it hosted with AWS. You can have it backed by Google Cloud Platform or Azure. It can be on any of those three. It really doesn't matter for our intents and purposes which of those three you use. Usually people just pick one of the ones that they're already using for their application. So if I was already hosting my server on AWS, I might use AWS for my Atlas cluster as well.
Doesn't Heroku use AWS?
Does what?
Heroku, don't they use AWS, or
if I remember right, they use AWS or Azure. You pick that cloud. I think you pick the cloud provider when you set up the instance, if I remember right. I think if I go into Heroku, it will actually ask me which of those to use as well. So you can use any of those three. You're not really going to see a difference for this course between any of those three.
So what does it look like? So do you just upload that JSON file? Is that how it works?
You can actually use, once you get it set up, you're going to end up with a connection string. Remember when we started this, let me disconnect. You see how there's a place to put in a connection string, and we just typed one in?
I think we just went with the default, right? Whatever was in there.
Yeah. So you can actually take the Atlas connection string, and you're going to put it in here, and then you just do all your stuff through here. Does that make sense?
Oh, okay.
Like, you don't even need to set up a local instance. If you're going to use Atlas, then you might as well just use it for everything.
Just build it in there and everything. How would you migrate it if you started it locally? Is it
I would just, if you started it locally, I would just export it, like I showed you. Export it to JSON and then upload it to the cluster.
Okay.
Upload it to Atlas.
And you can do that on the web, or you could do that somewhere else in the MongoDB.
You would do that through Compass. You'd do it through Compass to export it locally, and then you'd import it on there. If I go back in here, so you saw where we exported it.
Right.
There's this button. You just say import file.
Oh, all right, easy.
Yeah. It's just the same place. It's, there's your export, here's your import. So you'll want to create an account, and I think I already have one, so I'm just going to sign in so you can kind of see what it looks like once you get that account created. Let's see. I think, let's try that. Yeah. So once you get created, you'll come into here, this cluster. You may or may not have a cluster created already. I already do. If you do need to create a cluster, you just go to create new cluster. It's worth noting, you only need one cluster. Okay, your cluster can run a lot of databases. You can run easily 20 databases on a single cluster. You don't need to create a cluster for each application. Got it? Because only
0 it is.
Huh?
Cluster 0 it is.
Yeah. You will probably get charged if you have more than one cluster. There's a good chance of it. So, for your own sake, I would advise you just to create one cluster. So you're going to create that one cluster. If I click on here, I should be able to get in and see. So there's three. That cluster is made up of 3 nodes, basically 3 machines. And where do I get into? Oh, I think that. Oh, there we go. So I've got back up to the top projects, and I've got a few projects here, and they're under one cluster. Okay. So for instance, if I go into this project, that's on cluster 0, and then I can go into my collections. So yeah, I think you have to create a project first, and then you create the cluster, have the cluster underneath it. So project cluster, and so you'll just have one project and one cluster for this course. This will come up eventually. All right. So there, inside of there, you can see I've got a database, and then inside of that database is collections. Cool. So once you get that database created, let's see where I need to go back to overview, and there's a button called connect here. So you're going to say connect. By the way, make sure you create this as if you're creating this on AWS, make sure this is a M0 is the tier. So because that's, if I remember right, the free tier. So connect to cluster. They'll give you a few different options for how you want to connect. So if you want to connect through through Compass, which is what we've done so far, if you want to connect through your application, which would be Node, or if you want to connect through the shell, they'll give you kind of different instructions. So if I wanted to say connect to this database through Compass, I would go down here. I would say I have Compass. I've already got it installed. It asks you what version of Compass you have, and obviously we have the latest because we just installed it, so 1.12 or later. And so here's the connection string. Do you see that?
Yep.
Now you'll notice that the username and the password is in here is kind of faded out, so you'll have to type in those two and set that up yourself. Update the username and password then when you go to connect to it through Compass. But
I don't remember setting a password up when we went through. Is it default to this password?
I believe that you have to actually set one up. I think that initially it doesn't have a user on your database. So if you go down to security database access, so you have already created a user called PR Smith. But you probably will not have a user there yet. So you just say add new database user. They can connect and authenticate a few different ways: password, certificate, or IAM. These are beyond the scope of this course, so we'll just do the password. So password authentication, you can have it just auto generate one for you. Whoop. Password. I'm gonna have it generate one for here. Well, I may just have to go LastPass and have it generate one here. Generate secure password. There we go. So copy that. If I would put that in there, that would then have that permission. Then you just need to tell it that it's a read and write to a specific. So this would be read and write to any database in there. That would probably be the one you want to do. So you'll create that, and that's how you set up a user with a username and password, basically. Why is that one? That's going away. Okay, come back here. So specific.
That's your username, TJW.
Is that my username?
Well,
that is my username. I'm like, where am I putting in the username? That's what it is. That's what it is. So I might say test user, generate a secure password. That's what's going on. So test user, secure password, and then I would say read and write any database. And add user. There we go. So then you've got a username and password for them. Does that make sense?
Yeah, so how do you log in as one? Does it just do it automatically, or you got to go there and click on it?
So remember where we went to here, we had to hit connect.
Okay.
So you're going to go through here. This is going to give you the connection string. So you copy the connection string, go into Compass, say disconnect here. Can I dismiss that? I want to say new connection. There it goes. So there's where I would type that in. Connect. but it will fail to connect because I didn't type in the right password there, obviously. So I would advise you to go through, setting that up and using that as your way of connecting in. Pricing, just so you're aware, the free tier of Atlas, I think they say it lets you get up to you get 512 megabytes, and it says up to 5 megs. 5 gigabytes. I'm not entirely sure how that works, but you get there's a limit to how much storage you can get on the free tier. They then have the dedicated clusters. So if you were going to do this, use Atlas for a real world application, that's their pricing is $57 a month, is what that costs, which for, a hobby project is quite a bit, but for an actual real website is a real business is not that much. So that's usually worth it rather than trying to host it yourself. So we looked at Compass. Compass provides a GUI. It's run local on your machine, and it's kind of similar to Workbench, as you saw. For managing MongoDB, you can use that to manage either your local server or to manage an Atlas cluster or wherever else it's hosted. You just have to put it in the right connection string. There's also a shell available to work with MongoDB. So you can use that, for instance, with the terminal in VS Code to do any of these commands like insert records and look at records. So the way you get to that is Mongo sh. So that should already be installed. So there's basically 3 ways to connect. You can use Compass, you can use the shell. You can also use the drivers that they've implemented. The drivers are available for a lot of different languages and technologies. Here's kind of their list of everything that you can use to connect to MongoDB through code, and that are officially supported. So Node is the one on there that we care about this semester. So we'll be using the Node driver to work with Mongo primarily. So that's what we're going to use for our code. So in the next lecture on, I think Tuesday it is, we'll talk about how to use MongoDB, use the MongoDB driver with Node. Cool.
Sweet.
If you have any questions about how to get Atlas set up, just contact me and I can try to walk you through the setup process. But that's kind of the gist and the theory of how you get started and set up. And we'll talk about how to actually write code next week.